the opportunity to to mingle and work and collaborate and talk. So there's, there'll be lunch. Well, for now, there's breakfast and coffee. There'll be lunch. There's an outdoor space that we can use that's, just next to the breakfast space, the coffee space. There are also some tables and stuff here, and of course there are various collaboration spaces throughout the building that are open during the main part of the day. And so yeah, we're delighted to have Sewoong here. I'm sorry, I'm mangling the pronunciation of your name, but you can correct us. He is an associate professor of computer science and engineering at University of Washington, and also, I guess, currently what's your job? A scientist of some kind of yes. A good scientist at Google, and so we know Sewoong for his contributions to work on data privacy, or I know for a number of over the last 10 years he's been doing a lot of really interesting work. But more broadly, he has a lot of work in optimization and learning and information theory and how these things interact, and so he brings a really interesting also perspective with his work. And so we're really delighted to have him here. So with that, Sewoong, the floor is yours.
Thank you.
You've got an hour. So
I think, yeah, there's more time than I need, so. Right. So I'm probably going to be moving quite a bit, but I will try to speak loud so that I don't have to move the mic with me. And this is a joint work with my amazing collaborators at Google. Krishna, Alina, who's kind of local, Galen, Peter, and Brendan. And I was hoping that this will be more interactive than just me speaking, so feel free to interrupt me, raise your hand, speak up. All of those are welcome. So let's get started. All right, so about 1 year ago, I think some of us in this room were quite surprised when the following paper dropped, which said that at the time, the state of the art in MNIST was if you want accuracy like 98%, then you have to pay in privacy of epsilon about 3.0. So that was the state of the art. And this paper seemingly claimed that they have a new way of doing DPSGD, which would get them about 9% with epsilon 0.07, which is like 40 times better. And after a few weeks, people tried their algorithm. It was on the open source. And they figured out the following, that they were doing something clever about how they were doing clipping, but overall it was the standard DPSGD where you have a gradient descent with a step size eta, and you clip the gradient, average them over the mini batch, and add the noise, which is proportional to the sensitivity of the average, which is 1 over b. But how they were implementing it was there's a small honest mistake, which was that instead of clipping the gradient, they were clipping the normalized gradient, normalized by the size of the mini batch. Meaning now, the second one they implemented, the step size or the sensitivity would be 1 in this case, but they're still adding noise that's divided by the batch size. The batch size they were using was 4,000, so they were adding 4,000 times smaller noise than they were supposed to. And the problem is that, it's hard to detect such things because in privacy, one of the things is that if you have a bug, either in the algorithm or the implementation, you usually get better performance, which makes it really hard to debug. So to counterbalance this kind of honest mistakes, people are studying the following problem, which is auditing a given mechanism. So you're just given a mechanism A, whether you have the code or the algorithm or just the API, and then you get a black box access, let's say, to sample from the output of such mechanisms, and you want to audit it. And how people do in this standard setting is that you would construct 2 databases. One is, for example, like Fashion and NIST, which is the database that you care about, that you want to know the performance of, just to make sure that you're kind of auditing its use case in its native form. And Another example, another data set would be one that has one extra carefully designed example that's called Canary. So they defer only one entry as they should on the differential privacy. And you have an algorithm A that claims epsilon delta differential privacy. So what you do is you train either one of these models and pass it through the privacy barrier. And as an auditor, you pretend you didn't know which one it was trained on, and you try to do hypothesis testing, whether it was trained on one with Canary or without the Canary. And then you run it many times, get many samples of this outcome of the mechanism. And depending on how successful you are in this hypothesis testing, you... Sir?
Your laptop's still awake, yeah?
It's wide awake, yes. It died. Sir? It died again, so it... Should I do the whole thing?
I will contact someone, but that's for right now.
Okay. I guess I keep touching it or something. All right, so that's how you do it. You get many samples, and you try to see how successful you are, and that tells you how much leakage you have. And if you have too much leakage, you claim that the privacy is violated. Okay. Now I'm going to dissect this process of auditing to 3 steps and tell you how people are doing it right now, and then tell you how we plan to change each of these 3 steps to get better dependence on how many samples you need for auditing. So here we go. The first step is the definition of differential privacy, meaning that you start from the definition. I guess I don't have to say it, but I'll just say that this condition is with respect to deterministic data data sets D0 and D1, and a deterministic rule for deciding whether there is a canary or not in this case, which is represented by R. And for each one, you want to make sure that this condition is satisfied. And this gives whoever is participating, in this case the canary, the plausible deniability. It's on my emails. I can use any laptop. It doesn't matter what laptop I use.
Right, this is streaming?
Yes, it was just the same. Just this side.
Right. I think the idea that it's streaming might be part of the issue.
Anyone with the Mac that I have?
Yeah, I mean, I have a laptop that I use.
Yeah, well, no, we could try that.
But I suspect the issue is your computer. But do you want to keep maybe you can, while we're waiting for the slides, you can keep telling us
This is
about
where
it,
the
or-
picture gets really important. Just the moment where I was going to explain the picture.
That's the connection that I hear.
If there's a whiteboard, I could do it, but...
There are actually many whiteboards.
Is it?
All
I
whiteboard.
try.
Even marks.
No, the DAC's not going to do it. You're trying to dive, yeah. No. See that red light? Means we're not getting source. Yeah. So that's done.
So do you think changing the machine, the computer would?
Yes. Yes. Let's try that. So what do you say about the fact that the presentation is online? Don't. It could be intermittent data. Okay.
Your slides.
It's on my email, so it's picking me up.
Yeah, exactly. I'll do that.
That's direct. Yep, the one that's taped is going directly. So just coil that up and take that out. Can you download this locally?
Kill the Wi-Fi?
No, as in, can you download the file so it's stored locally on your
It is
computer?
also locally. Do you want, is there on the local? Do you want me
It's
to
the-
open the local one?
Yes. Opening.
So that's the local one.
So what I'm hoping the problem is if Wi-Fi it becomes spotty, and then the video signal becomes spotty, and it loses the connection to the system. That's what I'm hoping it is.
Okay.
Maybe
Yeah,
you
you're-
can play and see if it's.
All right, that's direct.
If I unplug here, it seems to help, but then again, another time it just came back on its own, so I don't know. Just trying to think of it.
There it is.
I'm gonna look at the restaurant again.
That's already, never mind. There, you've got slides temporarily. You can, why don't you finish logging in, and that way it's like ready as backup if this grabs out again.
Hear that?
Yeah.
That's the system engaging and disengaging for some reason. There's an intermittent connection going on.
Pitch it here.
Yeah,
Maybe
yeah,
I'll
yeah.
grab it.
Try it again.
All right, fingers crossed.
All right. Do let me know if it, if it goes out again. I might be watching you guys now. All right. Okay, let's get started. This is pictorial way of understanding differential privacy, which is very useful for, especially for this talk. So we're looking at the left-hand side as a true positive way, because there's probability there is, we say there's a canary when there was a canary. And the right-hand side is false positive way, because it's the case where we say there's a canary when there was no canary. And given any pair of databases, D0, D1, and the decision rule R, corresponds to a particular point that it achieves a FPR and PPR. And what it says is that those reasons better be satisfying that linear inequality, and there are two of it because there are symmetric version of it. Cynthia.
I'm so sorry with all the technical issues, but could you use the mic?
Yes, sorry about that. Too many things going on in my head right now. I'm worrying about the slide. Okay, so this is the DP condition presented pictorially, and for us, for this talk, it's going to be very useful in giving you the insights of what's going on. And when we say a particular mechanism A is epsilon delta differentially private, what it means is that that mechanism will have points in this region that it can achieve, which is represented as gray, and that whole gray region better be inside that red pentagon, then it's epsilon delta dp. And when we're saying we're auditing a particular mechanism, then what we're saying is that we're suspecting that the region of this mechanism A is outside of this red pentagon. And what we're trying to do as an auditor is find an evidence or counterexample of databases D0 and D1 and a decision rule R such that it's outside. So we don't know the gray region, but we know that blue point, and for sure we know that it's violating epsilon delta dp. So that's the starting point of this intuition. And in the second step of standard auditing, what people do is, now that we know we need to go find this evidence, how do we do it? So people came up with standard recipe for doing it, which is looking at a database that you care about, creating another one with one canary that's carefully designed, and then coming out with a corresponding decision rule or a test statistic. And what that gives us is an evidence that will achieve certain point. And if you have a strong canary, it means that it will be detected with high probability. So it's going to be more upper and left, which is stronger side, which is a good counterexample. If you have a weak canary, then it'll be more to the bottom to the right, which is a weak canary, which in this case won't be able to refute the claim of privacy. Any questions here? This is very important that everyone's on the same page here. Good. All right, and the third step is that we don't get to evaluate that blue point because we don't know the probability distribution of these mechanisms. We get it through the black box access to the samples of this outcome. So what do? We have a test statistic, which is an indicator function, and what we want, which is a TPR and FPR, are corresponding expectation of this Bernoulli random variable. So as we do, you go and take your favorite Bernoulli confidence interval, put it around TPR, which is y-axis, FPR, which is the x-axis, put it, and you get a square. So now you get a confidence square like that one, smaller if you have more samples, larger if you have less samples, and if the whole square fits outside of this red pentagon, then you're good. You've refuted successfully with the confidence that you want that this mechanism is not differentially private. All right. And we take the bottom right corner as the evidence because we're giving a benefit of doubt, and with the confidence interval, we're looking at the most private point and saying even that most private point is not private enough. Right, so standard approach to auditing is you create two databases, you collect n samples from each one, each time recording your test statistic that you said you would, and then take the average. Okay. One clarification, I was asked to use the local copy, which is a PowerPoint, which screwed up the, I don't know what else is screwed up, but it's reasonable. You can still make it. Sorry about that. Yes, and then you take the average and put the confidence interval, one for the x-axis, one for the y-axis, and you get the confidence square. So that's how people do auditing currently. And how does it work? There was a paper using this method, auditing the erroneous implementation of SGD that I said earlier. And what they did is they collected 200,000 models trained from scratch, each one, to refute claimed 0.21 epsilon delta differential privacy with sensitivity has an error of factor 4,000. And they show that epsilon is bigger than 2.79 with confidence 1 minus 10 to the minus 8th. So here they were being a little bit showy, meaning they didn't have to go all the way to 10 to the minus 8th, right? But they knew they could, and they wanted to prove their point. This is amazing work. But even if you go down to, like, say, 99%, I think you would need thousands of models trained, which oftentimes are too many. And what we want to do is understand why you need so many samples when you're doing auditing. So this is where the picture becomes really important. So on the left-hand side, I'm auditing a randomized response, which is binary output, flip with a coin with e to the epsilon bias. And if you're doing that, the area, this one is randomized response with epsilon 2, which let's say he claimed that it's with epsilon 0.8, and I'm trying to refute that claim. Then the regions look like that. This comes from that actual epsilon delta. And you got a big region to find your square, so I can use maybe 50 samples, I guess. The square is made up. It's not corresponding to 50. But if you have 50 samples, I think you can successfully refute that one. With the same claim of the epsilon and same achieved epsilon, if you go to Gaussian mechanism, now it looks like this. And this is what you're kind of fighting for or refuting against, because most of the mechanism we're building upon builds upon Gaussian mechanism at least. And if you add composition on top of it, I don't know, amplification by sampling on top of it, it gets flatter and flatter. And only the corner gets sharper. So if you had to, you need to really zoom in to just to be able to see the little sliver of space. And that's the space you have to fit your square. And imagine how many samples you need is like 200,000. That's why it's hard. And that's why sample efficiency in auditing is so crucial. And one thing is that during all this, like completely lost track of time. So please give me heads up if I'm like very slow. Okay.
You're like 25 minutes in, but you know.
Okay. Good. So prior work in auditing is what I explained so far. The next step, I think people had folklore kind of belief, and even I heard people ask this question during talk that Kalini gave on this topic, Nicolas Kalini, who's doing amazing work here in this space. And the question was something like this: why don't we add K-canaries, independently test them from each trained model and get K times more samples? Sounds very reasonable, but there's some problem, which is that what people have in mind when they talk about it is that you'll have two databases, one with now K canaries, and then you're testing for each one separately, averaging it, and that's your test statistic. Hopefully, if these canaries are roughly independent, the statistics are roughly independent, the variance will be K times, or square root K times smaller variance, and you'll get the gain in the confidence interval. But there's something wrong with this approach. Anybody want to tell me what's wrong? I don't
know. I'm not sure I even totally understand.
Sure.
When you said K canaries, I sort of expected you to say we're going to look for a violation of like a group privacy.
Right, that's exactly what I was asking for. Now, these two databases are K-hops different. So what you're actually looking for, the violation of is a group privacy, which epsilon and delta are about K times bigger. So what it means, again, from the pictorial point of view, is that that's kind of the status if you're adding one canary, randomized response, but you don't have enough samples, then the square is too big, and it eats up the red part, so it's not refuting anything that we're claiming. So you say, okay, I don't have time to go get more samples, but I do have time to add more canaries. So let's say I add two canaries, but as a thought process, let's say I added the same canary twice. And what that does is that it makes that canary stronger. It's easier to detect from the output. Now you added it twice, which means in this pictorial perspective, it's making it stronger. So the square is moving up and left. But it's not getting any smaller because you get only one sample from one trial. And also you pay for the group privacy because you have two hop different databases. The whole region you're trying to refute increases by K epsilon and K delta, which is slope becomes twice bigger. So you're not really gaining anything, but there's a little bit more wiggle room to find strong canaries. So there are amazing work by John that does use this to get stronger canaries, but statistically, it's not gaining you anything.
I have a question. Is it necessary? I mean, this would at best buy you like smallish constants, but is it necessary to estimate the two probabilities you're interested like separately, or could you just?
That's the second to last slide I have.
Okay.
So you'll have to wait 30 minutes for an answer to that. if it's okay with you, I'll defer. Yes, and short answer is probably not, but we don't know how to do it properly yet. And another way to do it is you might add two canaries that are completely different, distinct, independent, hoping that you get the statistical gain. Then you do, in the best case, will get a smaller square, but each canary is no longer no more stronger than the one you had there. So it'll be around the same region, just it's a smaller square. But you're still paying for the group privacy, so most likely you're not gaining anything. So it seems like there's no free lunch between having bias towards a stronger canary or having variance smaller so that you get a smaller square. So that's where the current status was when we started looking at the problem.
What do you mean by like the canaries being independent?
Right. So I'll give very precise examples, but for now, think about people adding random image and random label and calling it a canary. Then you do two that are independently sampled versus the same thing copied twice. I think that's a good, toy example to have in mind. I'll give you more precise examples with actual experimental results with it. Question?
Right, this might be a trivial question, but what happens if the probability, like if you draw a sample from the underlying distribution, the probability of observing K canaries is so small, so very in delta. Like I think by manipulating your data set, you might actually come up with a data sets that are so rare that they shouldn't really matter.
Right. Does it have to do with just the size, or are you talking about the distribution of the samples also?
Distribution of the
Samples. Well, canaries will look different from any other distribution by design. That's what it makes it strong. So you are putting in something from either backdoor attacks, data poisoning, something out of distribution anyways. So in that sense, it's kind of independent of the other distribution, the usual distribution, as long as you can find one that's different enough. It's true that the performance of all this is going to depend on everything, including the data set D0. If you can manipulate D0 also, you can get stronger canaries. But we're not trying to do that because in the end, we want to know if a DP model trained on fashion MNIST is private enough or not. And that's a slight variation between what you're refuting against. And we can have more, I think, offline afterwards, if that's okay.
While we wait for the situation to resolve itself, Mariam's asking like a good question though, which is you're basically saying like DP is this worst case definition over like all D0 and all like canary people. And if I'm a canary person, I'm a very strange looking person, and so maybe like nobody is particularly worried about the fact that canary people have their privacy violated because they're so conspicuous walking down the street with canary heads.
Right.
And there's like a really good question I think in this line of work, which is like sort of identifying how the amount of information leaked about like a person, like the canary, sort of depends on how much they do or don't look like people in MNIST. So like a random MNIST example is probably going to be kept pretty private because it looks so much like so many other samples. But in real data, people don't all look exactly like each other.
Right. So kind of answer, one answer we have for that is we're looking at an example where these are coming from actual humans. And then we're saying if I am worried about my privacy, then I'm worried if I do something really outside of the usual thing. I went to a website I usually don't go. I want that information to not be revealed by the trained model. So that's why the canary, I think we have a freedom of being very different and still wanting to be protected. And that's the mental model we have when we're building the systems, if that was a question.
But there is a big difference between like, a person with an unusual...
Right, totally, yeah. Still, it's a face is a face, right? You don't want to put something else and then say. Okay, so the fundamental question we're asking is, can we beat this, no free lunch bias variance trade-off and get the best of both? And we're going to show you how to do it. But let me first show you what we can achieve before telling you what we do. So we're going to add K canaries and do it in a smart way. And this is a kind of what we get in a 2 example, which is proof of concept. So we have a Gaussian mechanism, but I don't know it's Gaussian mechanism. I just have a mechanism and apply our method. And if you do what I said other people do, that'll be the blue line. And depending on how many samples you get, your square will get smaller. And then what I'm showing you on the y-axis is by fitting the tightest or the biggest triangle or pentagon you can fit, that's the largest epsilon you can refute against. And that's what we call lower bound on an epsilon. And I'm showing you that. And it gets, lower bound gets higher, which is better with more samples because the square gets smaller. You can imagine the slope getting bigger. And if you use our approach with k chosen to be square root of n for each n, there's a theoretical reason why we choose that. I'll get to that later. then you get this gain in the orange, which means that if you're refuting against something like 0.7, you get about 4x gain in the sample size needed to do that. And if you're against 0.85, then you get about 16x gain. And this is with Gaussian mechanism. So this is, for us, kind of the best case, the simplest realistic algorithm that we will be asked to do. And we'll have real examples coming up soon with trained models. Okay, so I said there are 3 steps in standard auditing, which is definition of DP and the conditions, designing one canary, adding data sets, and then putting Bernoulli confidence intervals. I'm going to tell you how we innovate on each one to get the best of the K-canaries. Okay. So in the definition, we're going to use what's called lifted DP, which means that now we allow the databases, which are one-hop neighbors, to be random also. So that we're allowed to add random canaries. And then I'm also going to allow the decision rule to be random. Okay. I'll keep talking while maybe someone can help me with this. So that it's called lifted DP because now we're in a lifted space where the data sets and decision rules are allowed to be random. And what we can show is that this is equivalent to original definition of DP, meaning that if a mechanism is lifted DP with epsilon delta, it's DP with epsilon delta. So it looks like we're not doing anything. But the main difference is that now you'll have exactly the same region, achievable region, and the condition, they're all the same. But the main difference is that each point now corresponds to randomized data sets, which allows us to use random canaries to search for a counterexample of evidence, and that's going to make all the difference. And step 2 is, so how do we design these random canaries in data sets is that we use leave-one-out construction, where we compare. Also, the goal is to be able to benefit from reusing K tests from each sample while keeping the data sets one hop neighbor away. So how we do it is first, I'm going to show you the construction with deterministic canaries and tell you how it fails and how randomization comes in to save us. So if you're doing deterministic canaries with leave-one construction, what it means is that your data 1 will have K canaries, and then you want to test it against each of the canaries, leaving one out. So it means that you need a null hypothesis, different one for each different hypothesis, leaving canary 1 out, canary 2 out, canary 3 out, so that you can run 3 hypothesis tests and average them and get the statistics. So you're not really gaining much because the null hypothesis requires K times N sampling, which you didn't gain anything. And how do we fix this is that you are going to randomize it with a specific randomization, which is you sample each canary IID from the same distribution. It's critical you do that. Because if you do that, now the resulting data sets, D1 and D0, with random canaries added in, are going to be random objects. And we're not comparing the instances of it, we're comparing the variables itself. And what we can do is generate one and think of a one with K canaries this way, and K minus 1 canaries this way in the other one. And because IID distribution gives you exchangeability in the statistical sense, the symmetry allows you to put this in the right context with lifted DP, because it didn't matter what you call canary 1, canary 2, canary 3, and so on and so forth. So with this, you can sample one training model from each one, and principled way run K different tests and get K statistics and average over them.
How do you choose the tests to run?
Right, so the tests and the canary designs are something that a lot of people are working on to make it stronger. And I'll give you examples of how to choose those, how to lift those single canary designs to fit our scenario is one thing. And specific test example is coming up in like next slide. So I'll answer your question next slide. So this is how we prescribe that you actually go and implement it. So you have n samples that you're going to take from this random training of models. And you generate at the beginning k canaries and create two data sets, one with k canaries in, the other one with k minus canaries in, which k minus 1 doesn't really matter. And then you train two models from each of these data set, k and k minus 1. And for the alternative hypothesis, k canaries in, you test for the presence of those canaries that were in there to get your true positive rate. Expectation of that is going to be true positive rate. And for the null hypothesis, what you do is you generate k new canaries from the same distribution because because of exchangeability, it doesn't matter which canary you test against as long as it's the one that was not in there. That's how you get k test statistics, average them, expectation of the quantity, the random variable is going to be the false positive rate, but variance, hopefully, is k times smaller.
I'm a little confused because like two things are changing between the alternative and the null. In one case, you're testing for things that are in the data set, and in the other case, you're testing for fresh samples from the population. But you're also going from like k canaries to k minus 1.
Yes.
And I'm a little confused why you need to do like the shift from k to k minus 1. Like,
Right. So I think that's in the definition of lifted DP. If you look at it, there is this expectation now in the condition over P, which is a distribution of D1 and D0, and they need to be with probability 1 hop neighbors apart. So we're designing a probability distribution over D0 and D1 that are coupled, but the condition only depends on the marginals of each one. So we're going after marginals, so we could generate fresh samples for D1 and D0 separately and estimate those probabilities. But in the definition, they're coupled. Hence the k and k minus 1. Coupled canaries, k minus 1 of them are shared, so they're in definition one hop apart. But in testing, we're only testing for marginals, so it doesn't really matter what the other one is. Like, I don't even have to generate the other one to get the estimated probability of one of them. If that.
but then wouldn't you want the R to be the same? I guess that's
So we need R only to be right.
it's distributed the same.
So there, I know why you're frustrated because I'm missing like a couple of steps in between because it's a talk and not a paper. So there is a way to start from this one, go step by step to the average one, which I'm skipping. So maybe we go offline for that one. Sure. I know why you're feeling like I'm missing something, which is true. I'm not presenting.
Maybe you can explain why I'm confused.
Right. So I'm missing some steps, and I can explain afterwards. But if you trust me, I think we can go with the talk. Okay. So it's important that I use lifted DP so that I'm allowed to use randomized canaries. And it's important that I use IID canaries so that I get exchangeability. And with that, I'm left to check for this condition. And the part you're missing is how I got this condition from the original lifted DP, which now it looks like average over tests, and then the tests now are different for each canary. There's a formal way to do it, which I'm skipping at this point. And what it gains us is when these tests are independent, we get a factor k gain in the effective sample size. In practice, they're dependent. We don't know the dependence. So the step 3 is how do we come up with a confidence interval for this now kind of multivariate Bernoulli distribution that are exchangeable but correlated and get the best out of it. So if you use first order confidence interval, which means I'm going to only use first order marginals of this distribution, you don't gain anything because your confidence interval scales like square root of the variance over n. And variance, if you don't have second order statistics, then you're just kind of using the worst case, which is TPR times 1 minus TPR, which is like order 1, so it's like square root 1 over n. So if you want to go a little bit higher, you can do second order confidence interval with estimating the second order statistic, in particular, the cross correlation between tests. And if you expand out that variance for our variable exchangeable variability that we care about, then you get something like this. The leading term is the cross correlation, and the second order term will be 1 over k, and the third order term will be the fluctuation finite sample that goes like the square root of the fourth moment over n. Okay? And what we're saying is that we don't have any control over cross correlation because that comes from the design of the Canaries, the sampling of the Canaries, the mechanism and everything else involved. We can observe it, and maybe we can measure it and put it in. And the best case, maybe that also goes down like the second order term, which is 1 over k. Then the best thing happens. We get a now confidence interval that scales like 1 over square root of nk plus 1 over n to the 3/4, which is strictly better than 1 over root n we could get.
Just so I understand what you're saying like you measure the cross correlation.
And put it in the confidence interval, right.
So you get like a valid confidence. You're saying like you will always get a valid confidence interval, but like if the correlation is what you expect, it will have to be.
It's adaptive. So if the cross correlation is order 1, you don't gain anything, and you get something that doesn't gain anything, but it happens to be smaller. You adapt to it, and that's important. And that's how you get the gain, for example, for the Gaussian mechanism that I showed you before, where in this case, you're just adding something in the Gaussian mechanism. Your test is an inner product test that people have already studied. And so we're not innovating on the skeleton of how you're doing it. We're augmenting it. We're giving some complementary to get better confidence in every case. And I said that it depends on the cross correlation. For this Gaussian example, I was wondering if we have good cross correlation. And it turns out that indeed, if you measure the cross correlation empirically with this Gaussian mechanism, adding random Canaries that's drawn random over the sphere, then you do get cross correlation that goes down like 1 over k, as we were hoping we would get. Gives you some, hope that this is a good thing to do. And as a guideline for the practitioners, when you're auditing, you get some freedom to choose, for example, the distribution of the Canaries for sure. Dimension sometimes, depending on the, if you can choose the size of models you're training, and maybe number of Canaries you put in there. These are the freedom that you have. And larger dimension always helps, for example, in Gaussian case, because the correlation gets smaller, like 1 over d, the performance gets better, the lower bound is higher in the orange. But in terms of Canaries, it's not as simple. We propose using square root of n because in the confidence interval, if you want to choose k, such that it's not too large, but kind of matches the other one, that's square root of k. It seems to work well. The green is how much gain you're gaining over the baseline of single Canary. So larger is better, and that kind of peaks around square root n in many examples that we tried. But it goes down when you add too many Canaries. And we wanted to dissect and understand what's the trade-off, and it turns out it's actually bias variance trade-off by adding more Canaries. What it means is that if you think about the distribution with more Canaries, then adding more Canary and testing for one of them means that the whole process has more randomness. So that acts as part of the privacy, making it more private. So that's why with more Canaries, you have a bias towards maybe, smaller epsilon, because it's more private. But more Canaries gives you gain in the variance of the confidence interval. That's the orange going up and plateauing. And between these two, you get this nice concave curve. Any questions so far? Salim? Right. So how we are kind of struggling and answering the question is that we are thinking of actually training a model with canaries in and releasing it. So that one will have good performance on fashion and mist, and will have passed our audit as is. So that's our goal. Have a model that passes our audit and also has the good performance on whatever the task that we care about. And canaries don't hurt the performance that much because they're completely separate, and the performance drop is within the error margin of the usual drop you get from differential privacy anyways. So that's the goal, why we have fashion and mist. And yeah, you could be as lax or strict in these goals as you want, but that's what we have in practically envisioning.
Oh, I see. So the bias and variance that you were showing us just now.
This is about epsilon, bias variance for the epsilon, the lower bound on the privacy. So accuracy is good. In most of the cases, it doesn't change at all with canaries or not.
The reason you want to just have like square root of n canaries is so that you want to actually release this audited model.
Right, the auditing is good. This is just the bias variance trade-off in the lower bound of the epsilon for the auditing. And all of them achieve like whatever the accuracy on fashion n is that you want to. Thank you for the question. Now I understand what's confusing. And then if you want to be fancy, you can go higher order confidence interval, estimate fourth order, put it in. There'll be like 8 terms, compute it, and to get, hopefully, theoretically, you do better. So with nth order confidence interval, your confidence interval scales like n to the 2m minus 1 over 2m. That's monotonically decreasing in m, but it's also diminishing return. In practice, the return diminishes so fast that it's not there after second order. So the fourth order one I drew, that's on top of the second order one. So it goes away pretty quickly. And yeah, the first order confidence interval is more or less the same as adding a single canary. Okay, I do have to check how much time I've got at this point.
So 7 minutes on the clock, but I mean, you've lost a lot of time for issues. So
No, I'm about 7 minutes left, so I think I'm good in time. But the video recording of this talk is gonna look so.
We'll fix it.
Yeah, we'll cut it in. All right, so now going to the real data, how do we use all the amazing things that other people have done to design strong single canaries and adapt it for our framework. We call it lifting the canaries. So what happens will be, I'll give you an example because there's no single rule for it, but I think it generally applies to any setting. So I'll give you examples. So this is a setting from this paper, which did, the baseline single canary design is, okay, they were trying to see if you can manipulate not the sample canary itself, but also the gradients. Why not? Maybe it's federated learning and you're retrieving gradients. Can you be stronger? So their canary is the following. Anytime algorithm touches the canary, it's going to return a gradient. That's something fixed with the norm equal to the clipping threshold in some direction chosen randomly, and it's going to be that kind of gradient update added every time, okay? Hoping that there's some consistency and then you can test it for later. How do you test it? Will be in the end, you get a model, you take the inner product with the canary and see how strong the correlation is or the inner product is. It's kind of straightforward, single case. And if you think about it, lifting it is kind of straightforward. You, instead of 1, you generate k canaries, IID on the sphere for the gradient, that are independent, but uniform on the sphere of norm equal to the clipping threshold. And you can do what we do. So this is what I mean by lifting, is that if you take how people do it single canary, there's usually a straightforward way to turn it into k canaries that are IID sampled. So blue one is what they achieve. It matches like what they report in their paper. And you do k canaries with k equals square root of n, and you get orange. So that's the instance gain you get without paying anything, essentially, paying the same thing. And over the k, this is square root of n, it's pretty kind of stable over the choice of large values range of k, what lower bound you get. If you go really down or really large, it'll be concave, just that we didn't, we look at it in hindsight, right? We run it and look at it, and then we know how we should have come lower and higher. So that experiment's probably all running right now. Krishna is running it. Any questions on the real experiment? Okay. Another example that people do, this is from John's paper from 2 years back, is called, I forgot the name. Something BKD, clip BKD, I think. Yes, for backdoored example. And there they do create a single canary with example X and Y, image and label. And how they do it is they look at the image space itself, I think it was fashion and mist, and then compute the SVD of all the images, put as a vector, and look at the least variant direction, so smallest singular value corresponding direction, and choose that as your image. Okay, so it's choosing an outlier in the image space, and then choosing the label, that's kind of the most unlikely, and that's how you design a single canary. And if someone tells you that's a strong canary, what we can do is we can lift it to k canaries by, in this case, instead of the bottom SVD direction, you take 300-dimensional subspace that are bottom in this SVD space and sample IID canaries from the 300-dimensional subspace and do the same thing. That's our lifted design. Kind of straightforward. And if you do that, this is the gain you get. This blue kind of matches John's paper, what he has. And orange is what you get instantly just by spending the same amount of resources. And k equals square root of n seems to be a good choice. Again, it'll be concave when you go all the way higher to the larger one.
So can you explain the difference between the left and the right?
Oh, okay. So left is over number of samples. And this is showing you how they change over number of canaries for particular fixed number of samples. So this, so this is comparing the performance. Here, I've already shown you the performance. Here, I'm showing you what's a good choice of the number of canaries.
Right.
And the dotted line is like square root of n, where n is 2 to the 10th. And that's kind of good choice of k is what
And
I'm.
on the left, little k is some function of n, the top.
K is square root of n is always the one we choose for all experiments, so that we're not, in hindsight, tuning for it.
And is that your dotted line on the right? Sorry.
That's the dotted line here. Yes.
Okay. Right.
Thank you for the questions. Okay. Yeah. So I only have 2 more slides, so since this is a workshop with like-minded people, I thought it would be good to pose a question and maybe get answers even from you later. So these are the things. So if you look at this one, this is good. This is the gain you get. And probably if you have a little bit more and larger samples, you can get more gains, it looks like. But still, the actual epsilon here is 4, and you're auditing like 0.2. And that's the kind of large sample needed that I talked about and how hard auditing is. So we need to do better in auditing. So what could we do to make it even better than what we do is what I want to poke your brains for. And here's one idea that was kind of posed in this paper, but not in a not completely answered, is that it's going back to Adam's insightful question, which is, why do you have to put a square there? If I could, I'd put the whole shape that I want, and I want that to be with high probability, not just the square. Is there any principled way, since that it's a 2-dimensional problem, it's not like 1,000-dimensional confidence interval, it's 2-dimensional confidence interval, can we do better? Maybe we can put a ball and that's better because corner will be cut, that's one idea, or maybe we can have some shapes that we can. So if anyone has insights to do better confidence interval, I would like to hear.
Okay, I don't have insights, but like a question. So, like one question here is like, there's another, like
corners.
extremes in the corners, you know, the bottom left and top right. And so it seems like rather than thinking of it as a single test, maybe it buys you something to think about. Or I don't know.
I think that's exactly related, for example, like this. Do we have to have the shape look like that? Or maybe we can have another shape and give a confidence interval of a shape that we want, in some sense, not exactly. So I think what you said is perfectly true if you care about the average statistics themselves, but when you start putting confidence interval with the confidence that you can like ascertain, then it's not clear how those will, you'll have confidence region, and that gets kind of to the question of kind of like this, right? Like what shape of confidence region you can
Right, but I guess
put around
like
it.
the qualitative question is like, it feels like what you have is a whole family of tests. And I wonder if by sort of ascertaining the performance of the family as opposed
Right.
to like a specific setting.
Right, so
Qualitatively change
right,
the kind of-
I think that's good idea, but how to do it with proper confidence is not immediately clear, is what
Right,
I'm
okay.
saying. Yes,
Yeah,
I agree with you, but I don't know how to do it. Is the way.
So the way I've seen it phrased, this ROC curve is often like related to this, you know.
FDP. People call it FDP for function f, that the shape, and there's all. Yeah.
This is maybe like sort of related, but kind of on a different angle. So instead of just the statistical question of like how do you kind of how do you get the number you report with statistical confidence? It seems like, you know, at least in the slides, I don't know if this is like in the work, you're sort of saying the one number I want to report is like the epsilon at a particular small delta. You know, but we also know that like for something like the Gaussian mechanism, like the best provable epsilon is very sensitive to that delta, or at least to log of that delta. And so like, kind of by definition, you're reporting these privacy violations in the super low false positive rate regime
Yes.
because like that's actually the only place where they exist. Like when you claim the Gaussian mechanism satisfies like epsilon equals 0.8
That's where it
instead of
matters.
2, like
No.
the only reason it doesn't satisfy 0.8 is because of this region. Do you have any thoughts on like maybe other ways you could like report these numbers that are more useful? Like, you know, some people say we should be reporting for upper bounds like the whole kind of Rennie curve, like of distant orders. So maybe the thing you actually want to be reporting is not like, is actually like the curve, like what, you know, some lower bound on the curve of like
Right.
epsilon.
So I totally agree with, I think, both of you that reporting the whole curve will be the most informative one, and you can, whoever gets it can do whatever the person wants to, and they can compare the curves and whatnot. I think it's something that's missing in all the literature right now is how do you bridge that perspective with, you know, statistical confidence perspective and put them together and come up with a meaningful resolution. So I think it's definitely a promising and important direction for practice, which currently is there's no agreed upon way to do it. Okay, so another way to make it stronger is that you get not only the last trained model, you in DP you guarantee privacy for every intermediate layer, model that you see in the training. And we're not using that in our experiments. So another way to make all these tests stronger is how would one test against all the intermediate models, knowing that the canary might have shown up anywhere in between in the mini batch in a random place. We don't know where it showed up, but we see all the models. So how can we use this information and the model's intermediate to make the whole thing stronger? So I think these are the two promising directions. Then one could definitely try and make our lower bounds higher. So in conclusion, we propose a new framework that builds upon this lifted DP definition, allows us to sample IID canaries, and put together with higher order confidence interval, gives you immediate gain. And because k equals 1 boils down to the single canary case, there's no loss, right? It's only strictly better because I can always If it doesn't, I can say I choose k equals 1. So it's only better, it gives you enough freedom, and sometimes it's quite, 16 times better. It's good. Another thing is that this is orthogonal to all the other people have efforts in making this thing stronger. So it can be augmented or complementary to anything that anyone has done in this space, I think. And I was planning to have the paper before my talk, but as usual, I'm 2 weeks late. So it'll be up in 2 weeks. Thank you. And if there's any remaining questions, I'm happy to take it.
Are there further questions? We've got slack in the schedule for questions. I guess I have maybe a general, a broader question, which is that this sort of like auditing by testing, empirical testing is kind of by definition hard in those regimes that John was mentioning, where you're sort of at the very, or like one of those two, both of the probabilities you're trying to measure are small. Is there a potential for some combination of empirical and analytical or like program analytical reasoning? Can we ask Bard to check our code and tell us what I'm being facetious, but like, it seems that there's also potential for something that's not entirely black box. Or even
Right. So I think it's important that we investigate the direction, and some people are, depending on complete black box to gray box to how much white box you are, you can do different things. So in practice, if you're actual practitioner who's releasing codes on these things and think how you should do it, you should cut your program into parts as the analysis is. For example, every maybe gradient update is a Gaussian mechanism with certain sensitivity, and that I think can be audited much better, especially if you know if it's Gaussian, because the curves that I showed you, if you know it's a Gaussian mechanism, then you are auditing against not the triangle, but epsilon delta Gaussian mechanism, which gives you a lot more room to audit against. So that's one direction that some people take, which give you much, much tighter guarantees. So there are many ways, depending on how much more you know about the algorithm, that can get you even matching upper and lower bounds. And I think some of those can be also complementary to what we do and can gain from both. But some others, there might be just even simpler ways to check, like Gaussian mechanism, you know it. Essentially, you're just checking for the variance and the mean of this Gaussian, which there are other simpler ways to do also. So that's one way, right? You can have a variance checker, mean checker, and then you do DP checking, just matching the table matching, and that gives you a certain guarantee every step, and that's already, I think, will be nicer to have. When that algorithm fails is if I know that's how you're auditing, what I can do is I can add a Gaussian mechanism on step 1, subtract it in the next one, add it on the next one, subtract it on the next one. For each step, it looks perfectly DP. If you compose it, it's DP as I want it, but essentially I added no noise. So, it can get dicier and dicier, but there are pros and cons to this. Yep.
Cool. Are there further questions? Well, let's thank Sewoong again, also for
PhD at UCSD, has told me that she's half Canary on her mother's side, and interested in privacy, fairness, all things responsible computing. And I'm excited to hear about this work on connections between replicability, privacy, and perfect generalization.
So thank you very much for the introduction, and thank you for the invitation. I'm super excited to be here. So today I'll be talking about connections between replicability, privacy, and perfect generalization. And this is a joint work with a whole number of co-authors, including some folks here at BU. So Marco, Max Hopkins, who's a grad student at UCSD, Russell Rexley, also a grad student, Tony Patassi, and Sachit, who's a grad student at BU. Cool. So the first thing I want to talk about today is replicability, what we're going to mean by it, why it's important. Okay, so replicability is relevant in all sorts of sciences and areas of data analysis. And to get us on the same page about what it means, I want to throw this cartoon of the scientific method up here for us to think about for a second. Okay, so how does science work ideally, and why is replicability important to it? Well, let's say we have a scientist, we'll say Dr. McNibbles here, has a hypothesis that they want to test, right? They think that some drug is going to be an effective treatment for disease X. So what is Dr. McNibbles going to do? They're going to go out, conduct some sort of experiment to collect data about the efficacy of this drug. And then they're going to perform some sort of statistical analysis on the data that they collect through this experiment. And then they'll conclude from this analysis that either the treatment is effective or it's not effective, and they'll ideally report their findings to the broader scientific community. And it should be the case, right, that if what we're doing is actually capturing a enduring phenomena out in the real world, it should be the case that another team of scientists could come along, conduct their own experiment to collect their own data, perform their own analysis, and obtain exactly the same results, right? And so that's what we mean by replicability. But as we all probably know at this point, unfortunately, the real world is not so simple as this cartoon. Things don't look quite as nice as we might like them to. So I'm not sure how much detail you can see here, but this is a chart from a survey conducted by Baker. It was published in Nature in 2016. It was trying to study the replicability crisis in the sciences. I feel like social sciences get a particularly hard time, so we're going to take one slide to beat up on the hard sciences for a second. So this survey asks scientists from the fields of chemistry, biology, physics, medicine, other sciences, have you ever failed to reproduce an experiment? Right, and this red bar up here is the fraction of respondents who said yes. You can see it's like over 50% for every discipline. The pink bar is maybe even a little bit more surprising. That's saying how many of them have failed to reproduce their own results. Okay, and again, we're looking at about like half, a little over half of scientists have failed to reproduce their own results. So what goes wrong, right? Like why can't we actually do science the way we'd like to on our little cartoon sketch? And there are lots of issues, right? And some of which I'm not personally equipped to talk about today. Some of them are, social issues. There could be issues of methodology or reporting of methodology. So maybe a scientist doesn't actually report the method that they followed, and so it's going to be difficult for another team of scientists to carry it out. There could be a statistical fluke in the data, and that's then sort of propagated through publication bias, where you sort of expect to see insignificant results appear as significant some fraction of the time, and then those are selected for by publication bias. And again, we're not going to be able to say anything about that today. We're going to be much more interested in the question of statistically invalid analyses, right? So there are issues of adaptive data analysis, and I'm sure folks are very familiar with here, issues of data dredging and p-hacking that can lead to results being reported as significant that aren't in fact, where we've in fact just overfit to the data. So in recent work with some co-authors, we introduced a notion of replicability for randomized algorithms, attempting to formalize some of these replicability issues and say when an algorithm won't be overfitting to the data, or can't be overfitting to the data. So we'll say that a randomized algorithm A is row replicable if for any distribution D, right? So it could be arbitrarily poorly behaved distribution. If I take 2 samples from this distribution, run my algorithm once on each sample, but I hold the internal randomness of the algorithm fixed between both runs, I should get exactly the same result with high probability, right? So we're seeing exactly the same output here. Okay. Any questions about the definition as stated? Okay, so a quick quiz to make sure we're awake. Let's say I want to design a replicable algorithm. I don't care that it's an accurate algorithm, I just want it to be replicable, okay? What is the simplest thing I could do? Yes, I can just take my sample, throw it out the door, and return a constant function, right? Let's say I want to do something a little bit more interesting. I don't want to be the constant function anymore. Again, still don't care about accuracy, want to be replicable. What can I do? Yes, I can output the randomness, right? So I sort of wanted to ask this question just to highlight that we're replicable for a fixed random string. Great. So this definition, oh yeah. I'm sorry, so we are going to require universal quantification over all distributions. We want it to be the case that, because frequently we're going to want to learn something about an unknown distribution, and so we want to know that we'll still be replicable even if this distribution is very poorly behaved. Okay, we can chat about it offline if you want. And
Maybe I can ask you, since you're mic'd, can you repeat the question?
oh yeah, absolutely, yeah. Okay, so this definition was inspired by a sort of similar flavor of definition called pseudo-deterministic algorithms. In this, they've sort of changed what's held fixed and what's re-randomized, but this is an interesting definition that's studied in the context of pseudo-randomness. It's also studied in an independent work of a group at Google, Ghazi, Kumar, and Manarangsi, and they introduced this under the name of pseudo-global stability. The definition is only trivially different in that they separate out our row parameter into 2 different parameters so they can reason about failure of replicability over random strings and over samples independently. And pseudo-global stability was in turn a generalization of global stability, which is introduced by Mark and some others in work studying private pack learning. Great, so today I'm going to talk about connections between replicability and other notions of stability that we know and love. So we'll be talking about connections to differential privacy, as well as connections to a related notion called perfect generalization. Now when I say connections here, all of these arrows indicate statistical implications. So what I mean by that is if there's a replicable algorithm that takes n samples, then there's got to be some other differentially private algorithm that is also sample efficient. So we're not saying anything about computational efficiency yet, but we'll get into that later on. So the plan today is first to do a quick introduction to replicable algorithms. It's a fairly strong stability notion, so I first want to convince you that they're actually achievable, that there are replicable algorithms for problems that we care about. And then we'll get into these connections to other stability notions. So I'll define all of the relevant notions. I'll probably skip privacy. I think everyone in the room is probably okay with privacy, but we'll talk about perfect generalization. And then also discuss a few applications about these connections that we get from these connections. And then we'll go through as many of the arrows on that diagram as we have time for. We definitely have more slides than time, so it can be like you all can tell me which arrow you're most interested in, or what separation you're most interested in. We can take a look at that. Great. So the replicable algorithm we're going to go through, hopefully quickly, is an algorithm for answering statistical queries. So the statistical query model is this model for learning. It's supposed to capture learning under random classification noise. And in this model, the learner isn't going to get direct access to labeled examples. Instead, they're going to interact with an oracle who has information about the distribution. They'll submit queries to this oracle and then receive back an approximation to the expectation of their query over the target distribution up to some additive error tau. And the great thing about this model is that we can implement such an oracle, right? If our queries are bounded, we can use concentration, just go out into the world, collect a large enough sample, and then use our sample to empirically estimate the quantity that we care about. And so we can actually implement these oracles in the real world. However, this becomes more tricky when we want to add the additional constraint of replicability, right? So empirical estimation isn't going to cut it for us anymore. So imagine we have the 0, 1 interval here, and the true expectation of our query is this green dot, okay? We go out, we collect sample S1, it gives us a slight underestimate, but still good enough for the task at hand. But if we go out and we draw another sample, then maybe it's an overestimate and we're not going to be replicable anymore. So there's sort of this 2 tau window that our estimates can fall in. So what are we going to do? We're going to subdivide our output range, 0, 1, into subintervals of width alpha. And now we're going to fix canonical representatives for each subinterval. And we'll return this canonical representative instead of the actual empirical estimate. So now we say, okay, the empirical estimate from S1 and S2 both fall within this P4 region here, and so we'll return P4, and we're replicable, and we can all go home happy, right? But not quite, because we can have this following case, right? Maybe the quantity that we actually want to estimate is right on the boundary. Okay, and so again, some samples will put us in the P3 region, some will put us in P4. We have a 50-50 chance of not being replicable. So what do we do? Well, we haven't used our randomness yet, right? I said this was going to be a property of randomized algorithms, and randomness is going to help us here, because we're going to use our randomness to pick where we draw the boundary for the first interval. Right, so we'll keep on drawing boundaries at width alpha, but we'll randomize where we start from. So now some randomness will be good for replicability, and some will be bad, but we can now bound the probability that we chose our starting offset within this problematic 2 tau region around the true value we're trying to estimate. Okay, so we're picking from a region of width alpha. We want to avoid a region of width 2 tau, so we can be replicable with probability 2 tau over alpha. Furthermore, this rounding is going to perturb our empirical estimate by something on the order of alpha, right? If we were like on the boundary and we round to a midpoint, that's going to incur some error in the estimate. And so we'll have to set alpha to actually be our target accuracy parameter, and then we'll use essentially a non-replicable statistical query for much tighter accuracy parameters, and use this to simulate our statistical queries replicably. So ultimately, at the end of the day, if we have target tolerance tau and target replicability failure probability rho, we'll need a sample size about 1 over tau squared rho squared. And this is a multiplicative factor, 1 over rho squared, larger than you would expect for normal statistical queries. Yeah?
Is everything in dimension 1?
For this? Yeah. And we have lower bounds as well, showing that this is unfortunately tight, that you have to pay this rho squared factor to get replicability. Cool. So that's replicable statistical queries. Any questions so far? Cool, we can get into these stability connections. All right, so again, I promised you we would talk a little bit about perfect generalization. Before I do, though, how many folks are already familiar with the notion of perfect generalization? Okay. Okay, so worth going into. Differential privacy, we'll start there, is a guarantee that's like worst case over neighboring data sets, right? We're not saying anything about a distribution. We're just saying you give me a data set, I'm going to take one element, swap it out for another one, and I want the distribution of my algorithm run on these 2 data sets. I want these distributions to be close. Perfect generalization is now introducing a distributional assumption, and rather than swapping out a single element, we're now swapping out the entire sample. Okay, so what we're going to say is, with high probability, for 2 samples drawn from the same distribution over outputs of the algorithm should be close. right? So this is sort of, you can think of it like a sample sort of privacy notion, but it's also called perfect generalization because it is a generalization notion, right? So the idea here is that if I have an algorithm that is perfectly generalizing, maybe its output generalizes, but I'm also guaranteed that future inferences made from the output of that algorithm will generalize. So it could be the case, if I have a non-perfect generalizing algorithm, it could output a perfectly good hypothesis that encodes the entire sample in its representation. And then subsequent analyses performed on that model could sort of read off the sample, and we could therefore overfit, right? If I have an algorithm that satisfies this perfect generalization notion, I know that subsequent analyses will still generalize. And yeah, I should have probably mentioned earlier, any place that I've written this like approx sub epsilon delta, I mean the notion of epsilon delta indistinguishability that's common in privacy. Great. So here's our diagram again of all of our connections. And now I want to say something about the efficiency of these transformations. So I'm going to put a little star next to every step of the transformation that also is an efficient algorithm. So notably, this step from perfect generalization to replicability is the only step that's not efficient. And here are the relevant sample complexities as well. So you can notice that if I start from differential privacy and I trace through the entire diagram, I'm actually not going to, all the way back to differential privacy, I'm not going to incur a huge sample complexity overhead. Right, so each line is blowing up by sort of at most a quadratic factor in the original sample complexity of the algorithm. So I promised you a couple of applications. I've picked two of my favorites, but there are some more in the paper. So one is applying the path through our diagram from privacy to replicability to obtain pack learning algorithms that are replicable for all sorts of problems, really for finite hypothesis classes. So we have private pack learning from the cleaners result. And then because we have this transformation from differential privacy to replicability, we now have replicable pack algorithms for finite hypothesis classes that only has a logarithmic or polylogarithmic dependence on the hypothesis space. So cool, we can learn things replicably. It's kind of exciting. And now if we trace through our diagram again, starting from differential privacy, and go through perfect generalization through replicability, and back to privacy, we can convert a private algorithm into a private algorithm, which sounds silly, but I haven't said anything about the parameters that we can get out of this yet, okay? And the cool thing about converting a private algorithm to a private algorithm through this little triangle here is we can actually sort of get privacy amplification for this delta parameter that we want to be very small, and where we'd ideally like our sample complexity to have logarithmic dependence on this delta term, right? So if I start with an algorithm that has, let's say, the delta term is like 1 in the sample size cubed, right? Ideally, I'd like that to get that down to something like exponential, and I can do that through this conversion to a replicable algorithm, and then going back to privacy. Okay, so hopefully I've convinced you at this point that this diagram isn't just a cool thing to have, it's also a useful thing to have, that there are reasons we should care about the connections between, yeah?
When you do the transformation, and let's say for replicability to then what you get is still replicable, or you lose replicability in order to?
Yeah, so you lose replicability. So we're going to sort of like compile it. We're going to like run the replicable algorithm multiple times.
Can you get something which is all free?
I think that's an interesting question. Yeah, I think it's a. I guess. I think it's an interesting question. Maybe. Do you want to say something, Mark? Oh, sorry, you mean like what algorithms can we apply this to, or sorry?
Yeah, because I mean, presumably you're allowed to change the algorithm in some of these implications because they're taking in inputs of different sizes. You're changing the sample size. So, like one trivial way to convert a perfectly generalizing algorithm to a replicable one is to turn it into a constant function, right?
Oh, sorry, I see what you're saying. Yeah. So I've sort of like suppressed dependencies on like failure probabilities here, but that is because the sample complexity overhead will be like sort of logarithmic in accuracy parameters, and I think we do have to be a little bit careful about assuming good enough accuracy of the starting algorithm, because let's say I have a replicable algorithm with bad accuracy, then I can end up sort of amplifying incorrect responses of the algorithm. So you do need to be like accurate enough to start with.
Okay, accuracy is always for like some family of statistical queries, or is it for?
Sorry. Oh, okay. Maybe okay. So this is for general statistical tasks, if that's what you're asking. So this applies for these transformations apply for general statistical tasks, with the caveat that the output domain of the task, or that the algorithm has to be finite. Does that answer your question? I'm sorry, I forgot to repeat it out loud. Right, so I guess what I mean is we're going to assume distributions here, and we're going to assume that distributions sort of induce good responses, that there's like for distribution a set of good responses.
Some kind of like relation between distribution and
Yeah, and we're gonna be like very loose about what that means. We're not gonna say like, oh, there's like an L2 ball containing all of the good answers or something like that. We're just saying that, yeah. Does that answer? Okay, great.
Thanks.
Yeah.
Let's see, I guess I have two questions. One, queuing closely to what Talil was asking about. Why does finiteness of the output space matter? Does that appear in those sample complexities?
So it will appear, I guess it appears in a couple of places, but most saliently in this arrow from perfect generalization to replicability. So this is, spoilers, this is going to work by correlated sampling over the output domain of the algorithm. And actually defining correlated sampling, I think once you move outside of finite ranges, gets a little bit tricky.
But is it like, is there a term that is like, in the sample complexity, there's a term that is like, the size of the output?
Oh, no.
Like that, it just, like, does finiteness impact somehow the quality of the transformation, or is it just sort of like something you need to make the analysis work?
It's something you need to make the analysis work. Like it's not an issue of like, oh, we're gonna have some sort of intractable sample blow up. In fact, there is no sample. There is a version of the conversion from perfect generalization to replicability where there's no sample blow up whatsoever. I guess if you want like weak replicability parameters, but to sort of like define the conversion, you need this finiteness. Yeah. So I guess you can imagine if I wanted to do like a correlated sampling, again, sort of like skipping ahead if I have two distributions that are close, I want to use a single random string to sample from both and get the same element. I could do this by rejection sampling. I could use my randomness to pick an element from the domain, and then return that with probability, with its probability under the distribution. But then to even sample that element for rejection sampling, if I have like an infinite output domain, I need access to infinite randomness to even do that. So.
Right. My second question is it feels like this would probably apply to even much more general notions of algorithmic stability than just this sort of epsilon delta. Is that true, or is the kind of multiplicative notion implied by this sort of epsilon delta closeness, is that a key to this whole diagram working out, or could you use other notions of stability, of distributional stability, like just total variation distance, or
So this is a great question, and I'm not sure, I'm gonna seek Mark's advice for how much I should say about this, but if you check archive over the coming week, there's a paper that is not ours that should be showing up that looks at TV indistinguishability and using this instead of perfect generalization, though I should say perfect generalization, or I should say TV indistinguishability is sort of an instantiation of perfect generalization for a particular setting of parameters. But yeah, I guess correlated sampling as a primitive normally applies. You normally say, okay, I'm going to get the same output from a correlated sampler with probability that's proportional to the TV distance between the two distributions. And so anything that I can use to get a TV distance bound between two distributions will be sufficient for this last step here.
Yeah, so it's not sort of super tied.
No. Though again, this is also just the format of like theorems that I know about for correlated sampling. You could imagine more exotic things that, right, have, yeah. But yeah, we just need close distributions. Any other questions? Okay. Great. So let's start getting into the actual transformations here. Okay. So I'm going to start with how we go from replicability to privacy and perfect generalization, since this is what I consider to be sort of the easier direction, and in fact, the replicability to privacy direction was already shown in a sort of more restricted setting in this work of Ghazi, Kumar, and Monarangsi. And both of these transformations work very similarly, so I'm going to treat them as one, focusing on the conversion to differential privacy, and sort of waving my hands aggressively and saying a similar idea will work for the conversion to perfect generalization. The argument, though, is quite a bit more technical and involves some more work. Okay, so we're starting with a replicable algorithm, and we want to get a private one. So replicability is going to tell us that, there are many strings, such that if I run my algorithm with that string and two different samples from the same distribution, I should get the same output. Right? So what I'm going to do is take a larger sample, larger, by this factor log 1 over delta over epsilon, and I'm going to partition it into subsamples of the size required by my replicable algorithm. So we'll say size m. Okay, so I'm sort of using this table here to describe the partition. So I have partitioned my sample into S11, S12, et cetera. Okay? And I'm going to run my replicable algorithm a whole bunch of times on all these different samples. But I'm going to fix the random string in each row here. So I'm going to pick one random string, run it a whole bunch of times. I'm going to try another random string, run it a whole bunch of times. And why am I doing this? Well, replicability tells us that with high probability over samples and randomness, we should get this replicability property, but there can be bad strings, there can be bad samples, right? And so we want to sort of like hedge, make sure that we're going to be picking a good random string, and so we're going to just try a whole bunch of them, okay? And because we're partitioning our sample, if we want a private algorithm, so we have to consider, okay, well, what happens if we swap out one element of our sample? And what happens is, well, there's a partition, we're just going to change one of the subsamples here, one of the partitions, which means we're going to change exactly one of the outputs of our algorithm. And so we can now apply a private selection algorithm on top of the outputs of our replicable algorithm here, use that to select a good output and return this. Okay? And the idea that private selection should work and have good utility so long as the most common output, there's a common output that is very common. And replicability is going to give us that. Right? It's going to give us that there's some output we see with high probability. Cool. So let's talk a little bit now about privacy to perfect generalization. This proof is sort of technical, and I don't, at the moment, have a great idea for how to make the math very illuminating. So I'm instead going to steal an example that I think gives a good intuition. that I am stealing shamelessly from my brilliant co-author, Sachet, who originally used this to sort of motivate why we might think differential privacy should imply perfect generalization. And I'm in fact going to show something like fairly weak here. I'm going to consider a specific problem, consider a specific pure DP algorithm for it, and show that this algorithm is just automatically already perfectly generalizing. Great, so the problem here is estimating the bias of a coin, given m flips of the coin. So I get a sample, which is just going to consist of some ones and zeros representing heads and tails. And what is my algorithm going to do? It's going to sum up all of the xi's here and just take the average and add some Laplace noise. And my claim is that this approach is actually already perfectly generalizing. Okay? So why do we think this should be true? So let's think about what happens when we draw two samples from the same distribution. Again, right? So we're thinking about generalization, so we're going to have this distributional assumption now. So we're assuming we're seeing two sequences of coin flips from a coin with the same bias, as opposed to differential privacy, where we're just swapping out a single flip for another one. And because we're drawing two samples from the same distribution, we can apply concentration, right? So that's sort of immediately what we're going to do here. We're going to observe that with high probability over two samples of coin flips, it should be the case that the difference in their sums is, again, with high probability, less than square root of m, where m is the total number of flips that we observed. Okay. Now, if with high probability over two samples that's true, then it's also the case that I could imagine permuting the observed flips from S prime to get a sample that we'll call S tilde that has Hamming distance less than square root of n from S, right? So I'm just sort of like rearranging this sample to get things to line up. And notably, again, I'm just permuting things, so the average is exactly the same, and therefore the distributions, right, of I get from running A on S prime and A on S tilde will be exactly the same. Cool. So you can see sort of what that might look like here, right? So we just rearrange and like, hey, look, these are actually neighboring data sets. Now, if we only have a bound of square root of m, we can't actually do like a bound of 1. They won't be neighboring in the normal sense of differential privacy, but we can, because we have a pure private algorithm, sort of absorb, we can still apply privacy and say that, okay, we're going to be epsilon square root of m private. So then to drive this epsilon square root of m down to the epsilon we like, we just blow up the sample complexity. Okay, so we have this algorithm for the coin problem. It's private, and then also if we just take a larger sample, it will be perfectly generalizing as well. Any questions about this? Again, this is just sort of meant to motivate, why we should expect it to be true, that we can go from a sort of worst case over neighboring data sets assumption to an average case over trading out samples sort of notion of stability. So in work with Cummings, Legitnism, Roth, and Wu, they showed how to apply this intuition for more general tasks for pure differential privacy. And then in our work, we show that this is in fact also true for approximate differential privacy. To give like a little bit of a peek into how this is actually going to go, we go through an intermediate definition. But I think we've seen enough definitions today. We don't need to spend too much time on this additional one. But it's a nice notion, and it's one of max information. So it's looking at the amount of information essentially that the output of an algorithm reveals about its sample. So there is already existing work, Rogers, Roth, Smith, and Takar, that show that approximate differential privacy implies bounded max information. And so we use this with privacy amplification to get the parameters we want. And then we show that we can convert this into perfect generalization. Cool. So we're back now to our diagram. We have about 20 minutes, so I'm going to keep on trying to get through as many arrows as possible before I'm dragged off stage. So let's look, we've talked about this a little bit already, this conversion from perfect generalization to replicability. And we said that we're going to use something called correlated sampling. All right, so again, the idea here is that constructions do exist, but one, they're definitely not always going to be efficient. And our results will only hold if our algorithm has finite range, right? We can't really define this procedure otherwise. And correlated sampling is this primitive and was sort of studied by Broder, Kleinberg-Tardish, and Holenstein. And the idea here is that we have some representation of a distribution, say QD, and we're going to use randomness R to sample from it. So a correlated sampler will take the representation of the distribution, take a random string, and it should be the case that one, the correlated sampler actually samples from the distribution that you gave it to sample from. But it should also be the case that if you have two distributions, two representations of different distributions that are close in statistical distance, and I feed the same random string into my correlated sampler, one run with the representations of these two distributions, I should get the exact same output from my correlated sampler with probability that's proportional to the total variation distance. So about as good as you could hope to actually get. So we're sort of like coupling distributions by randomness here. And also note that, again, the Google group, Ghazi, Kumar, and Manarangsi, used correlated sampling as well in some of their work on item level, user level privacy. So how are we going to apply correlated sampling? Well, we've already sort of talked through this, so maybe I'll try to move through it fairly quickly. The idea here is that perfect generalization is giving us stability, right? So if I have two different samples from the same distribution, again, I want to get replicability, so I want an algorithm that, if I fix the randomness, will give me the same output with high probability. So I will first run my perfect generalizing algorithm on its input sample. And again, if I consider running it on two different samples from the same distribution, this perfect generalization gives me closeness of the resulting distributions. I can sort of leverage this into a total variation bound as well. And now I apply my correlated sampler on top of these distributions. And so for a fixed random string, I'll get the same output with high probability. And it's really, just how this conversion is going to work. And so the question is, when do we actually have efficient correlated samplers for a particular problem, right? So the approach I mentioned before of this rejection sampling might work if I have like a very high entropy distribution, but if all of my distribution weight is concentrated on like one particular point, I'm not going to sample that point with high probability, so it will take forever for me to actually return something. So it won't be computationally efficient. Great. So yeah, we've now gone through replicability to privacy, privacy to perfect generalization, and back again. So we've actually managed to cover all of the arrows. I'm very proud of us. Which lets me now talk about the fact that not all of the steps in these transformations were computationally efficient, right? We had this correlated sampling step isn't necessarily efficient, and so this is sort of keeping us from being able to do everything efficiently. And this raises the question, okay, like did we not try hard enough? Are there maybe like other things we could look at other than correlated sampling? And the answer is probably not if cryptography exists. So if public key cryptography, specifically a kind of public key cryptography that's called re-randomizable, which is achievable through standard cryptographic assumptions. If this kind of public key cryptography exists, then there are in fact statistical problems that you can efficiently solve with a private algorithm that you can't solve with replicability, and that they would break the underlying public key crypto system. And I think I have time to go through this, so let's give it a shot. So here's the problem that I claim we can solve with privacy that we can't solve replicably. I'm going to have my re-randomizable public key encryption system. and I'm going to fix a public key for this crypto system and fix two distributions, D0, D1. D0 is going to be the uniform distribution on encryptions under my public key of the bit 0. Okay? And the other distribution is just going to be supported entirely, uniformly, on encryptions of the bit 1. Right? And your job is, given a sample from one of these two distributions, not to distinguish between them, because that would be hard. If it's a good crypto system, you should not be able to, but to just output a ciphertext that encrypts the same bit, okay? So you don't have to decrypt anything, you don't have to do any distinguishing, you just have to do something to your sample and output a new, fresh ciphertext. And in fact, you could just, a solution to this problem without privacy or replicability would just be to pick an element of your sample and return that, right? That would be a valid solution to this problem. Cool. So what is the private algorithm for this? We're going to get a sample, and we'll say it's, they're all encryptions of a particular bit B. I'm going to augment my sample. I'm going to pad it out with, again, this is a public key crypto system, so I can encrypt things myself. I'm going to pad it out with encryptions, some encryptions of 0, pad it out with some encryptions of 1. And then I'm going to pick a ciphertext uniformly at random from this new augmented data set, and I'm going to apply my re-randomization procedure to the ciphertext. Now, what the re-randomization procedure guarantees me is that I get a new ciphertext encrypting the same bit, but it's not going to carry in information about the starting ciphertext. I'll have a uniform distribution. I will get sent to like a uniformly random ciphertext encrypting the same bit. Does that make sense? Okay. Great, so I'm going to, again, pick a bit, re-randomize it, and output that, okay? And again, the idea here is that first of all, if I have two neighboring data sets, then the probability that I even sample the element that I swapped out is pretty small. And then also that I'm getting this uniform distribution over ciphertext encrypting the same bit. And again, like I said, this re-randomization procedure exists from some pretty standard cryptographic assumptions. The Goldwasser-Macaulay crypto system, for instance, is randomizable. So what's the issue now if we try to do this replicably? Let's assume we could do it replicably. So first of all, we should already we should sort of expect we shouldn't be able to do this, because the idea of replicability is that random strings induce canonical representatives, and canonical anything is generally going to be pretty bad for cryptography. You don't want things there to be canonical representatives. This makes distinguishing tasks easy. And that's what we're going to leverage here. So imagine we have this algorithm A. How are we going to create an NCPA adversary from it? Again, the idea here is that our adversary's job is, given an encryption of a bit, we don't know the bit, to return a good guess for the bit. Okay, so we start with our encryption, and we're going to run the re-randomization procedure a whole bunch of times to generate a new sample of encryptions of that same bit. Okay, so again, we kind of have a whole fresh sample. Encryptions are entirely supported are entirely of the same bit, and we can now run our replicable algorithm on this sample. We're at the same time going to generate a second sample, and that will be encryptions of the bit 0, right? And again, we're going to get a whole sample of random encryptions of 0. Run our replicable algorithm. Again, if we think of a replicable algorithm as inducing canonical representatives, it should be the case that if the encryption that we got for the NCPA game was encrypting a 0, we should get the same output with high probability, right? So we can just check that. So we say, okay, we had a sample where we knew the bit, we had a sample where we didn't know the bit, gave it to our algorithm, did it give us the same output? If so, the bits must have been the same. And that's the idea here, right? So we're just, if, again, we have re-randomizable public key cryptography, then this separation is sort of inherent. At the same time, we also show a result showing that if one-way functions don't exist, then you can always do correlated sampling efficiently. You can invert everything you like, which allows you to do this correlated sampling. Great. So that's it for the connections and separations, and I'll just take a minute to go over some questions that I think are particularly interesting. So first of all, there's a question of what are the right cryptographic assumptions for the separation I just talked about. I showed that, okay, if one-way functions don't exist, we can always do correlated sampling, and so that whole diagram is computationally efficient. However, if randomizable public key cryptography exists, there's this inherent separation. So which is it? Is it public key cryptography, or is it like one-way functions that are actually required for the separation? I'm also interested in trying to get better adaptive composition for replicability. So replicability does compose. However, for each additional, for each query that you want to make, you're going to lose a factor of rho in the overall replicability. And so if I want, target replicability rho and I want to make k queries, then I'm going to have to set the target for each query to be rho over k. I can expect to pay a quadratic factor in my replicability parameter to actually answer these queries. And so I'll end up with paying sort of like a k-squared factor for adaptive composition. And through connections to privacy, it'd be nice if we could actually get something that's closer to k times rho instead of k-squared rho. Also interested in trying to understand when this conversion between differentially private algorithms and replicable algorithms can be made efficient, right? So it seems reasonable that there are problems for which we can do this. So there's the correlated sampling issue, but maybe there's something else that we can do that doesn't go through correlated sampling, or even just being able to characterize the kinds of problems, right, that where the conversion breaks down. I'm also interested, we started this whole talk thinking about science and replicability in the sciences, and then sort of quickly shifted to more TCS types of questions. But I do sort of want to get back to trying to solve problems in the sciences. And it's frequently the case that if I'm actually trying to replicate someone else's experiment, I'm not going to draw my sample that I'm using for replication from the same distribution, right? Time has passed, that distribution is gone. But maybe it's similar, and so I'd like to be able to get some of these same guarantees that we get for replicability under two samples drawn from similar close distributions, but not exactly the same. And that's it. Happy to take any questions. Yeah, I like to call it our one weird trick. I wish I could, so it underlies, I think, most of our algorithmic results in some way or another. There is a similar thing for half spaces. We have replicable algorithm for half spaces that does something similar, where you can get sort of different parameters or running times depending on how you want to chop up d-dimensional space. But yeah, eventually, like at some point, we are going to chop up d-dimensional space and then pick canonical representatives from your partitioning. So I would love to have additional tools in our toolkit, but I think we either use those as building blocks for a lot of things, or just use it directly. Yeah. So are there other techniques there where we can maybe steal ideas from them, or do you think it really is sort of like this is maybe in some sense necessary?
I could throw one out, although it's not, I don't think it would affect the kind of theorems you're showing, but like, if you try to implement some of these ideas for adaptive data analysis, to allow adaptive data analysis, often the simplest thing to do is to have one data set with which people do whatever the hell they want, and another data set that's used for verification of results.
I like the holdout.
Much smaller, right? And a particular version of that is that actually turns out to be like implementable and work pretty well in practice. Is like that holdout data set you only ever allow revealing a single bit about it, and it feels like maybe some idea like that. It's sort of like an extreme version of the kind of compression type approach to generalization, where you have a very small possible output space. Maybe there's some idea, which it wouldn't, I don't think it would get at any of the sort of very general conversions here necessarily, but like, it could be that like maybe what you want to do is sort of have replicability only of like some very simple final question, and then you don't necessarily need like the whole complexity of like a much more complex algorithm.
So actually, I'll sort of riff on this just because it gives me a second to talk about ongoing work that I'm very excited about on trying to apply this notion in the setting of reinforcement learning, where instead of having a sample being labeled examples, or samples are now the results of transitions, exploring an MDP, and I think like one of the maybe like the selling points for having this strong notion of replicability is like even if at the end of the day we really we just care about sort of downstream, like the very last decision like sort of replicability. In trying to come up with replicable RL algorithms, we so far haven't been able to do any better than sort of starting further upstream, right? So sort of stabilizing exploration, and from there getting replicable policies. And so I do think it's like sort of interesting, when we're talking about like stability generally, to figure out, okay, well, how far sort of upstream in coming up with a model do we actually need to start aggressively stabilizing the algorithm to guarantee that the results will be either replicable or generalizable or whatever your objective is. Yeah.
I want to follow up on a question that Adam asked earlier in the talk, which is about the sort of robustness of all these sort of connections to exactly how you measure closeness of a distribution. It seems like it's quite robust. I mean, it seems like you do need in several places like this kind of delta, total variation freedom that epsilon delta gives you. But I'm trying to think, like, what does, it's interesting that replicability is like this one parameter definition. There's only the row, and the row it's not a negligible quantity, right? You think of the sample complexity is
Yeah.
a polynomial in 1 over row, so it's kind of more like epsilon than like delta. But the delta seems necessary in the other formulation, in the other definitions that you're showing equivalent to. So I'm wondering, is there some like one parameter analog of approximate DP that's sort of suggested by replicability?
So okay, I don't know that this is going to directly address, but I will say an observation that like rhymes with sort of what you're saying is that if we don't try to do anything fancy, and we just apply replicability to try and get differential privacy without trying to do any sort of like amplification along the way, the row does go sort of straight into the delta term, right? Which is to say, like if we didn't have like a matrix when we were doing our conversion from replicability to differential privacy, we just had a single row, then it would go straight into the delta term. But then, yeah, I guess like through being clever, we can sort of tighten things up a bit But yeah, I don't have a good answer. I'm sorry.
Speculative question.
Yeah. Yeah.
Can you say a little more about this limitation to finite output spaces? Are there examples where, like, if the output space is infinite, that this kind of equivalence breaks? For instance, an example I would love to see, I don't know if it can happen, is we know that with differential privacy we cannot learn threshold functions over the reals, but could there be a replicable algorithm for learning threshold functions over the reals?
So I would say no, if only just because of the top arrow that would then give us DP algorithms. What do I want to say about the limitation? I will say, like, check archive in a week for generalizations too. So there's like work on sort of extending correlated sampling for not finite ranges, but for countable domains. But I think an issue is sort of like in a sort of standard computational model, I don't know how you get away from needing just infinite randomness, right? So at some point, right, if I want to sample from a potentially infinite domain and I want essentially my, randomness to tell me pick out an element, then I need, I'm not sure how you get away from that. Sorry.
Is this like the same question as like how do you sample from a Gaussian or something? Like, is that the same class of question that we don't know the answer?
I might appeal to Mark. Do you have a good answer to this? I don't think I do.
I imagine you can, look at these idealized real arithmetic computational models and be able to state and answer some of these questions if you wanted to be more careful about things that way. I think it's really a matter of, like, we just didn't do it.
Yeah, I think we discussed, like, briefly, like, other computational models or sort of like generalizations of replicability where algorithms only have to, like, share some finite length of randomness. But yeah, I think that with the computational model we were considering, it's just, yeah, I don't know how to move away from it with what's already known about correlated sampling. Yeah.
Wanted to ask like a less technical question. So you mentioned early in the talk that there's this kind of unavoidable cost to replicability. At least, for statistical queries, you need this blow up, right? In most scientific fields, samples are expensive, extremely expensive, and so, actually, like so I guess my question is, the broad question is, like, maybe we shouldn't be shooting for replicability. And if you sort of look at what, many scientists expect from replicability, it's not exact. It's not that every time you get the same result, or even most times you get the same result. It's sort of like you get some notion of broadly similar conclusions, where broadly similar is sort of a fairly flexible idea, and it's like domain specific, right? And so I wonder if that suggests that there's a kind of a more relaxed goal. Like, maybe the TCS language would help us formulate a more relaxed goal that is achievable without such a huge cost in sampling costs. Like, even m to, okay, 1 over rho, that's a big cost. M to m squared, that is I would, like, quibble with your description of the
Oh, yeah. But it's a small polynomial.
It's like an enormous,
Okay.
Right.
Yeah, no, that's fair. That's fair.
Small enough. Yeah, I'm not trying to tease too much. But, like, maybe there's something else we can shoot for that's more modest and that is still sort of
Yeah, so actually we've been talking about this a little bit too, and I'd be very curious if folks had ideas for possible relaxations. One thing we've been talking about is trying to see if you can get anything by saying, okay, well, rather than sort of requiring that the models be exactly the same, what if we just require that with respect to the distribution, they're functionally equivalent, by which I mean they give the same output on like all but an epsilon fraction of the distribution, right? Or if like for a regression setting, let's say that like their classifications are within some tolerance tau of each other on all but an epsilon fraction. That seems already, right, like a yeah. And like, but yeah, I don't know that we have any examples yet of cases where this allows you to circumvent the lower bound that we have for instance, statistical queries. But yeah, I'm definitely interested in that because again, like I think like from a theoretician standpoint, I was like, oh, it's just this multiplicative like 1 over rho squared. That's not so bad. And like again, now that I'm working with RL people, they're like, this is awful. Like, trying to actually implement these algorithms, they're like, we need to do something about this. So trying to see if are there some like structured distributions where if we don't have to have this like universal quantification over all distributions or something can let us get around that lower bound.
Like, never mind RL, if every sample is a cancer patient. That's fighting for very small numbers. Anyway.
I think we can take other questions offline. Let me thank Jessica again. Have lunch until 2, which I'm assuming. Yeah.
So we're delighted to have Jelani Nelson here for our third talk of the day. Jelani is a faculty member at UC Berkeley and we're very happy when he was in Boston to have him over here, on a somewhat more regular basis to give talks, and so that was really nice. But now he lives further away, so we get him more seldom. He's done, of course, lots of great work on many different areas of algorithms and computational learning. But today we're hearing about this other branch of his work. And so let's welcome him. Jelani, you have the floor.
Okay, thanks. Okay, so this talk is based on, I guess, 2 different works with subsets of the people I've written there, namely Hilal Asi, Vitaly Feldman, and Kunal Talwar, who are all at Apple, and Hui Nguyen, who's at Northeastern. And also, before I start, let me say if anyone wants to ask questions because we're being recorded, please use the mic in the middle of the floor so they can get you, or if you don't want to, I can repeat your question so the mic catches it. Okay, so this is going to be about local DP and focusing on two problems in particular. So first, let me just start with like some motivation. So probably all or most of us have smartphones, and there are certain features we like on our smartphones, like, for example, autocomplete or automatic spell correction. Okay, how do these things work? Well, here's a patent. I don't represent any company. I'm just showing you something I found on the web. Okay, and if you zoom in on the abstract, it says, systems and methods are disclosed for a server learning new words generated by user-client devices in a crowdsourced manner. So what does it mean? It means they're learning from our data, right? So those things are coming from training some ML models. I don't know exactly how they're doing it, but they need data to train those models. That data comes from us. Okay, so yes, they're using our data. So what's the setup? There's a server, which is like the phone manufacturer or whoever else. They want to know something about our data. So for example, they want to know the word distribution amongst devices. So let's say for each device, what's the last word that you texted your friend? Okay. It could be some other data. It could be like, what's the most frequent zip code that you spend time in when you're using your device? Okay. And then now you can imagine creating some histogram based on the data, where F is this histogram, and F sub X is how many devices are holding data item X. The last word you texted is X. And simple enough, right? Each device sends a copy of all its text to the server. The server knows everything. What is there to do? But this is the privacy workshop, and they care about privacy. So do you really want the phone manufacturer to read all your text? Probably not. And in fact, if you go back to that patent, they know that themselves, and the patent abstract is littered with mentions to privacy and differential privacy, local DP. Okay. So this is, given my audience, you already know this, so I'll go through this quickly. So we want local DP. Each device basically is going to send a random message that is only weakly correlated with its data, such that from the perspective of the server, it looks like random garbage almost, but they can extract some utility from the aggregate. So we're using the standard pure DP definition for this talk. I won't spend time on it because you all know it. Well, actually, I think everyone here is a privacy person. Should I even bother reading these definitions? Probably not, right? Okay. What? Oh yeah, local DP. Anyone? Okay. Does anyone want me to spend any time on this slide beyond? Okay. Oh, I see what you mean. Oh. Okay. I see. Yes. Okay. Okay. Good. So yes, the usual two regimes: small and large epsilon. Large epsilon is usually what's deployed in practice. By large, I just mean like 5 or 6 or something like that. And of course, the reason is that because there's a fundamental trade-off between utility and privacy. And it turns out that for the applications, this is what I'm being told by people who are closer to the applications for this specific work, that small epsilon requires too much utility loss to be useful for them, so they need large epsilon. But the silver lining is that if you do things like shuffle, that automatically improves privacy. So I'm not going to talk about shuffling in this talk, but the punchline of this slide is it's okay to use, it's okay to get away with epsilon being 5 or 6 or something. Okay. And we're going to focus on the regime of epsilon being much bigger, bigger than 1 in this talk. Okay, so I'm going to talk about two problems mostly today. And the first problem is this histogram estimation or frequency estimation. So what's the problem? It's the one I said. There's a finite domain of size k, and each device, I, holds some xi from that domain. Now there's a frequency histogram, and the server wants to recover an f tilde that is close to f, say, with mean squared error. So I want to look at, say, the average square distance between the true frequency of x and the estimated frequency of x, basically the L2 norm squared. It's a random variable, right? F tilde is random because the messages are random, so I want this to be small, say, an expectation. And for me, this is mostly an algorithms talk. We're going to say what the problem is we want to solve, and then we're going to talk about designing an algorithm that solves it efficiently. So what are our criteria? So, what are the things that we want from our algorithm? There's the usual privacy utility loss trade-off, yes, where utility loss is this mean squared error. But I also care about other resource issues, right? The devices send messages. I want those messages to use as few bits as possible. I want the server to be fast. The server aggregates these end messages and has to run some algorithm on them to figure out what f tilde should be. That algorithm to compute f tilde should be fast. And the device also should be fast to, conditioned on my data, sample my message according to this LDP protocol. Okay. So ideally, all these things on the slide, these 5 things should be as small as possible. If you fix the other 4, ideally want the 5th thing to be as small as possible. Okay. And maybe there are some trade-offs. And we want to understand the trade-offs. Okay. So just as a warm-up, let's just talk about a scheme that I think you all have seen before. And let's just understand what does it give you and what does it not give you? What is there that we want to improve? So randomized response, right? What does it mean? Each device sends its true item with some probability, e to the epsilon p. Otherwise, it sends a uniformly random other item. There's only one value of p where this makes sense, because the probability you send something is 1. Right, so with probability, there's only one item that has probability e to the epsilon p, my true item, and there are k minus 1 other items, each with probability p, so p, solve for p. Okay, so now what the device does is determined, and what does the server do? In this talk, we'll just look at a simple thing it could do, which is a natural linear unbiased estimator. So it wants to estimate for each x, how many devices do I think are holding x? So what does it do? This is the linear estimator, the unbiased estimator. For each message it gets, if the message is x, I'll add alpha plus beta to a counter. If it's not equal to x, I'll only add beta. Okay? And notice that if the ith device actually was holding x, the expected, you always add the beta to the counter, and you only add the alpha if you actually sent x, which happens with probably e to the epsilon p in case 1 and p in case 2 where you're not holding x. So these are the expected contributions. I said I wanted an unbiased estimator. It means that I want the first thing to equal 1 and I want the second thing to equal 0. So it's alpha and beta are unknowns, 2 linear equations, 2 unknowns, solve for alpha and beta, and you get what alpha and beta need to be. So this completely determines the protocol, right? I've told you what the device does. I've told you what the server does. And now we can just look at it and see, is it good? Okay. The pros. Low communication. There's basically no overhead. I mean, sending my actual element would take log k bits. It's an element of a domain of size k. My message is also log k bits. And it's linear time for the server, and it's also constant time, depending on your model, say for the device. The con is that if you actually compute the expected mean squared error, which is basically something like some variance computation for each fx, the mean squared error is pretty bad. And I'll write down precisely what it is later, but just take my word for it, it's bad. It's bad because we're in a large domain setting, right? K, I'm imagining K is very large. If it's binary randomized response, then fine, but we're in the setting of large K. Okay, so now, actually just maybe, okay, so I imagine everything I've said so far is stuff that people have seen, maybe, in this audience. Just out of curiosity, I guess, subset selection, who's seen that for LDP? Okay, so now maybe I'm getting to stuff that many people haven't. Okay, so it's also a pretty simple protocol for the same problem. So now each device sends a random subset of the domain of size d. And then there are going to be some sets that are like voting for x and those that are not. So if x is in S, so now for each, there are k choose d. There are k choose d different subsets I could send. Of those k choose d subsets, the ones that contain S, right, which is, I guess, k minus 1 choose, the ones that contain x, there are k minus 1 choose d minus 1 of them. Those will have probably e to the epsilon p each of being sent. I'm just defining what is the distribution over messages. And those that do not contain x, there are k minus 1 choose d of those. Those will each have probability p. Okay? And again, there's only one value of p that makes sense because the probability that I send something is 1, so p is whatever it is. Okay. So now how does the server estimate the frequency of x? Same as before. If the message I get from a user is a vote for x, namely x is contained in that message, the message is a set, I'll add alpha plus beta, else I only add beta. I can again write the expected contribution if a device actually is holding x versus if they're not. I want the first thing to be 1, I want the second thing to be 0. And now, solve for alpha and beta, you get a protocol. Okay, just like before. Okay, but the only thing that we haven't set yet is d, right? If d is 1, this is just randomized response. Okay. but we're allowed to set D to be larger if we want. And so how should I set D? Well, if I'm trying to optimize utility, I should basically pick D so that the mean squared error is minimized. So if you do that, I'm not going to do the calculation on the slide, but all it is a calculation. You write down the mean squared error, you get an expression, you do some calculus, you choose D optimally, and it turns out that the D that minimizes the mean squared error is D that's like the integer closest to this number, k over e to the epsilon plus 1. Okay, so now what about this protocol? The big pro is that it's actually up to a 1 plus little o of 1. So not just big O of optimal, but really it even gets the optimal constant factor. It gets the optimal utility loss for a given epsilon, the optimal mean squared error. Okay. The downside maybe is, if you think about what it means to pick D this big, your message sizes are huge. Your domain is of size k. You're sending almost the entire domain in your message. So your message length is k bits proportional to k bits, as opposed to randomized response, which was log k bits. So the communication is exponentially worse. And just because the messages are so big, it also means the runtimes are worse, because the server has to read these giant messages, and the device has to construct this big message and send it. Okay, good. And I guess one thing that I'll remark at this point, which I didn't fully absorb until I started working on this project with my collaborators, is, as a usual TCS person, I just think big O is great. As long as you get big O of opt, or even big O of tilde of opt, you're done. As you'll see later when I talk about some other prior work, people actually knew how to get big O of opt utility loss, like up to a factor of 2 even, with linear runtime, with log k communication. Everything was fantastic. But the thing is, if you have big O of fast, if you have an algorithm that's big O of fast, you can speed it up. You can get the constant factor better by parallelizing or throwing better machines at it or whatever. But if you get big O of opt utility loss, that's not something you can improve by spending more money on compute, right? So, for example, my collaborators, in this paper who are in industry, they say, oh, actually, we really prioritize accuracy of the downstream model that we're training for whatever task, and that's directly connected to the utility loss. So, we're willing to sacrifice, having the fastest algorithm if it means we can actually get better utility loss. So ultimately, what we care about is kind of not sacrificing utility loss, but still getting everything else to be great at the same time. Okay, and now let me lead into our mechanism, the new contribution of this work. And before that, let me mention a meta approach, okay, which both randomized response and subset selection are special cases of, which is that, look, there's a message space Y. In randomized response, it's just like the message you send is an element of message space, right? So in randomized response, it's the domain itself. In subset selection, it's all subsets of size D of the domain, but it can be generally whatever you want. And I'll associate with each element of the domain a subset of messages in message space I'll call S sub x, which I'll call the preferred message list. And I want these preferred message lists to form a design. Namely, they should all be the same size. And if you look at 2 elements of the domain, the intersections of the preferred message list should be small. And it should always be the same. It should be the same, and it should be a small thing. Okay. And the mechanism is, again, given that your data is x, I need to assign probabilities to each message of being sent. If it's not a preferred message, it's p. If it is a preferred message, it's e to the epsilon p. Again, there's only one value of p where this makes any sense. Okay. And then the server does the same thing before. So it either adds the alpha plus beta, or it adds the beta. It only adds the alpha in there if it got a preferred message. Okay, so any questions? I see some people still reading the slides. So if there are any questions, let me know. Okay, so yeah, this is all just like before. You need to make sure that you have an unbiased estimator, and then solve for alpha and beta, and you get some alpha and beta depend on the parameters. It depends on p, which implicitly depends on the size of message space, as well as this intersection size L, and the set size is S, whatever. There's some closed form thing you can write down. Okay. Yeah.
Question about the previous scheme, I think.
Subset selection?
Yeah.
Mhm.
So one way to implement it would be to, or actually, I guess this is sort of like a meta thing that you can do with lots of different schemes, like have a potential output be chosen pseudo-randomly, and the actual respondent really is only generating like one bit that, so for example, like if D were K over 2, I think I'm getting the parameters right,
Mhm.
D were half the universe,
Yeah.
then you could imagine that like somehow pseudo-randomly we generate a candidate set,
Yes.
and I just tell the server whether or not to use that set or its complement.
Sorry, in what you're proposing, is there shared randomness between me and the server?
Right. So.
Okay.
So then, so then if you kind of approach it that way, then with shared random, if there were shared randomness, you wouldn't be any further communication other than that one bit. Or in general, one could imagine communicating like a seed,
Uh-huh.
which could be a lot shorter. And
Yes.
I guess some of these schemes
They do that.
can be basically interpreted that way.
No, I mean there is one scheme called Pi rapport. PI stands for pairwise independent. That was by I think Kunal and Vitali, maybe in ICML 2 years ago or something. Which is basically taking one of these, not the scheme that I showed you, another scheme rapport, and like applying some de-randomizing it and sending a seed. It sounds similar to what you're saying. I'll mention it later when I have a results slide, which has all the kind of the table of what everyone gets. And so the nice thing about that is it improves the communication because you only send the seed, but their runtime is still slow.
By pseudo-random, you end up expanding.
And yeah, it wasn't clear how to implement their thing as quickly, but
All right.
yeah, okay. I should maybe also say one thing about public randomness, which is not all protocols that use public randomness are equally nice, and the reason for that is compatibility with if you want to deploy this in the shuffle model. So, yeah. Okay. Good. So now now that you know the protocol and you can try to analyze it, and it turns out that the computation of the mean squared error only depends on these parameters. It only depends on SL, the size of message space, NK epsilon, et cetera. So if you do that computation, which this slide is only to show you that you could do it in a slide if you really wanted to, but okay. I'll just say that the thing that ends up, can you tell that this is blue, by the way?
Tell it's blue. I can't figure out parse much else about it.
Oh, yeah, okay. So the only thing I'll say is that the dominant term in the mean squared error is this blue thing. Okay, so which maybe you can't read. Okay. So what I will say, I don't know if you can read the red thing, but if you fix all the other parameters, this blue thing is an increasing function of L over S. It's also an increasing function of Y over S, where Y is the size of message space. So kind of it gives you a hint as to like what you need to do to get something that's optimal. And then also, now that we know from prior work that subset selection is optimal, it gives optimal utility loss, you could go back to this expression here and say like, what did subset selection do how did subset selection behave on this blue thing here? Okay. And if you go and do that, try and get that understanding, what you find is that basically, L and S were chosen so that L over S cancels this e to the epsilon minus 1, and also Y over S is also equal to e to the epsilon minus 1, and then you end up getting like 2 times e to the epsilon minus 1 times 2 times n, so you get like 4n something in the numerator. Okay, so you kind of know what you're shooting for, and you know how one scheme got it. Okay. Unfortunately, that scheme was inefficient with communication, et cetera, but you know kind of like what you're aiming for. Anyway. So now it's completely a combinatorial design question, right? I want to design a set system. Oh, yeah, please. Oh, I can repeat it for you, yes, okay.
L was the size of the intersection of the messages?
That's
For two different things, what was S?
Oh yeah, okay. The question is like, what is S and L? So, yeah, up here. So we have this domain of size k, and now, at the end of the day, we're designing a set system with k sets. Okay. Each set is a subset of message space, which we can make message space be as big as we want. And each of those k sets has S elements. And if you look at the intersection between two different sets, the intersection size is exactly L. Okay, so yeah, does that answer? Okay. I should also say, we know from this that we want L over S to be small, and we want Y over S to be small. We also want Y to be small, just by itself. Why? Why do we want Y to be small? Just so we're all on the same page. Yeah, so exactly. Because the communication is log Y, so we want Y to be small. Okay, good. So, so now this is a common Sorrell design question with some algorithms. Like ideally for us, we not only want S and L and all this stuff to be good, but at the same time, it has to come with a fast algorithm, right? That we can actually compute all the things we need to compute quickly. Okay, so. So you think about it, you don't know, combinatorics is hard, you don't know what to do, so maybe you stop and you pray or something, okay, you turn to religion, and then you realize that actually, religion was trying to tell you something, okay, which is that this, painting was drawn in perspective. So it's like, oh, you should actually use projective geometry, okay. So you use projective geometry, and okay, so what does that mean? Okay, so, what it means is that your message space is, okay, we're going to fix this a little bit, but first let's start off with this. Your message space is fq to the t, where q is some prime. We'll see what q needs to be in a second. And we'll pick t large enough so that the size of message space is at least the domain size. Basically, t has to be the ceiling of log base q of k, right? And then now, since there are more messages than domain elements, we can view every domain element as an element of message space. We can just pick some kind of injection. Okay. And then what I'll define the preferred messages for x as to be all the vectors used such that x dot u is 0 mod q. So it's the t minus 1 dimensional subspace orthogonal to x. And then now, so now let's think about what is the intersection of sx and sy. So it means u dot x has to be 0 mod q, and u dot y also has to be 0 mod q. So it's a t minus 2 dimensional subspace, right? So that means that S is q to the t minus 1, L is q to the t minus 2. We kind of know that these things need to cancel. We know what we're shooting for in that expression, that blue expression from before. So we should just basically set those things to both be 1 over q and set q to be the thing we needed to cancel. So pick the closest prime to e to the epsilon minus 1. So for example, if epsilon's 5, e to the epsilon turns out to be roughly 150. So you'll pick like 149. Q will be 149, okay? Good. So that's it. Except we're not quite done, and the reason we're not done is this is not a valid design, because what if y is a multiple of x? Then actually sx intersect sy is not t minus 2 dimensional. It's still the same subspace, right? So this is where you now do your projectivize, and you use your projective geometry. So all that really means is, okay, so yeah, I'll skip this slide, but I got really I didn't know a whole lot about drawing in perspective. Like I didn't really, obviously I knew of this photo, or this picture, but I didn't really understand why it was such a big deal, or why was the Renaissance a big deal at all. It just looks like any other painting, okay? So I got a deeper appreciation for art by working on this LDP stuff. So, but yeah, so here's some stuff about art, which I'll skip for now. But projective geometry comes, it's related to drawing in perspective anyway. So we'll define projective points in fq to the t as non-zero vectors whose first non-zero is a 1 as you scan from left to right. So you see a bunch of zeros, and then eventually you see a non-zero. The very first non-zero you see should be a 1. Basically what it means is, take your vector in fq to the t, which is not 0, and just divide it by a scalar so that the first non-zero entry becomes a 1. Okay? So these are your canonical points. So every line has a canonical point. Okay. So the number of projective points is something. It's that, q to the t minus 1 over q minus 1, y. You subtract 1 in the numerator because you got rid of 0. And then every non-zero vector has q minus 1 ways you can scale it by a non-zero scalar. And then you identify the domain with projective points. So pick the smallest t such that that's at least k. And your preferred message list is your message space now is projective points. Your preferred messages is the projective subspace orthogonal to x, namely all projective u such that all canonical vectors u such that x dot u is 0 mod q. Okay, so this is the new setup. And like you can go and compute S and L and all that stuff as before, and you're happy, everything works. Okay. So this is a table. I don't know if the font is too small. Let me pretend to be you. I don't know. Okay, sorry. Maybe I'll just say some highlights from the table. So if you look at randomized response and look at the utility loss, there's some stuff, but the thing to note is that there's an n times k. N is a big number. It's the number of devices. K is also a big number. It's the domain size. So it's big times big. Okay. Whereas if you look at something like subset selection, it only has the n in the numerator, not multiplying the k. So I'm happy. And then you look at subset selection, look at rapport. They have the optimal utility loss, but the communication is bad. It's proportional to k, and the server time has an n times k in it, which is also bad. If you look at pi rapport, which is, I guess, similar to what Adam was talking about with, can you use pseudo-randomness? Pi rapport tried to do that. They used some pseudo-random approach, and they got the communication down to roughly log k instead of k, basically only sending a seed instead of having to send a lot of stuff. Utility loss was the same, but the server time was, again, either k squared or n times k. Actually, one of the things that we noted in this work was there is a way to implement pi rapport faster than the pi rapport paper said, but it's still not quite as fast as what we're going to be able to get with this projective stuff. Okay. And then you have these two mechanisms, Hadamard response and recursive Hadamard response, that if you look at their utility loss and compare that to subset selection, they're only off by constant factors, right? A factor of 2, so 8 instead of 4, or a factor of 9, I guess, 36 instead of 4. And they have great communication, log k, and they have almost nearly linear time on the server side. But they don't get the correct constant in the utility loss.
Is that epsilon here, we're supposed to think of it as a little bit bigger because it's LVP?
Yeah, think of epsilon as bigger than 1. Yeah. Like a small constant, but but small, medium size, I don't know, okay. Not smaller than 1. And then you can see what projective geometry response, good communication, optimal utility loss, and the server time, it's not quite as fast as, say, Hadamard response or recursive Hadamard response, because there's an e to the epsilon there, which, if you think of epsilon as 5 or something, you have like 150 multiplying your k log k. And then we also showed that there's a way to trade off. If you really don't like that e to the epsilon multiplying your server time, we showed that there's a way to trade off utility loss for server time. So let's say you pick some other prime q, that's any prime that's at least 2. You can replace the e to the epsilon in your server time with q, but then your utility loss gets worse by a 1 plus 1 over q minus 1 factor. So for example, let's say you choose q to be 5. It means that your utility loss will be 25% worse, so it'll be 5n instead of 4n. But your server time will only have a 5 there instead of having an e to the epsilon there. So you can do, that's a trade-off you can do if you want to do that. Okay. Okay, and we also implemented, I think, every scheme you see on this table. We implemented them all, and we ran some experiments. Let me just explain what these curves mean and what the axes are. So, of course, these mechanisms are all randomized. So your mean squared error is a random variable. So we wanted to get a sense of what is the CDF of this mean squared error random variable. So we ran an experiment like 1,000 times or something, okay? And even though those lines might look like lines, they're not. They're actually dots plotted 1,000 times each. So because they're so dense, it looks like a line. But you can actually tell with the blue one, there's like a dot that's kind of by itself on the right side. These are just like the empirical errors, right? So the x-axis is the percentile. The y-axis was the mean squared error. So like if you look at the 50th percentile, that's the 50th percentile empirical mean squared error. And in the left plot, RR is randomized response, which is the thing that's really bad when it comes to mean squared error. So it's kind of like so bad that it makes it hard to tell the difference between the other ones. So on the right-hand side, here's another experiment where we just didn't run it. We did not run it with randomized response so that you can actually tell the others apart. And you can see SS is subset selection. That's the dark blue. And light blue is our new thing, projective geometry response. And they're like kind of close to each other, right? And then yellow is the hybrid version of our algorithm where you trade off runtime for utility loss. And we did that with cubing 5. And you can see it's like, it is worse, but slightly worse compared to, say, Hadamard response or recursive Hadamard response, which are the red and the green up there. They're like noticeably worse. Okay, yes?
So what is like varying across these percentiles? They're percentile of what?
So it's like, okay, so we did the following simulation, right? There are n devices out there. We gave them each a data element, and we said, now each of you send your message according to the local randomizer to the server, and the server collects all these messages, computes f tilde, and then we look at the mean squared error. We look at f tilde minus f L2 norm squared, right? That's a number. And it's
so these are percentiles like across runs. So
across, yeah. Exactly. Yes.
3/4 of the executions had that.
3/4 of the exactly had that error or less.
Okay, so like the median error for the blue and purple is like identical.
Yes.
Somehow there's like more variability.
That's correct.
In the error.
That's correct. That's correct. Yes. So yes, that's right. So the median errors for light blue and dark blue were basically the same, but yeah, the shape of the distribution was not the same. And then just more and more experiments. There's kind of this consistent picture. If you look at the black labels at the top, we tried different kind of data distributions where Zipf and decay in terms of like look at this histogram. What does the histogram look like? Is it a spike histogram? Is it kind of uniform? Is it Zipf decay or whatever? And we tried different ones, and it kind of didn't really matter in terms of the picture. They always roughly looked the same in terms of comparing the mechanisms against each other. Okay. So let me just just more and more of similar kind of looking things. We also did a timing experiment. So we said, look, let's look at a domain of size 3 million. Let's choose epsilon to be 5. And then, let's run different mechanisms on the server side. So it's like so each device sent its random message to the server, and the server had to then aggregate those random messages and then compute f tilde. How long did it take it to compute f tilde? So for pi rapport, which is this low communication, optimal utility algorithm that was the state of the art before, and we actually even implemented it with our new algorithm for pi rapport, which is faster. It still took about half an hour. Whereas our algorithm took 37 seconds. The hybrid version of our algorithm took about 6 seconds. And those are slower than RHR or HR, recursive Hadamard response and Hadamard response, but they have the better utility loss, right? So it's like, maybe you're willing, it's still much better than half an hour. It's not as good as a second or half a second, but you're getting optimal utility loss, so maybe you're okay with that. One thing that I will mention, which is a little bit annoying, and I'll leave it as an open problem, is if you notice, I said basically you need your domain size to be you need your message space size to be at least the domain size, right? Q to the t roughly should be at least k, which means t should be the ceiling of log base q of k. That ceiling is a little bit annoying because if you're like just barely below an integer, you have to round up, and rounding up just means that all the computations you're doing are over things that are like a factor q larger than you really needed them to be. And q, like if epsilon is 5, q is 150 roughly, right? So it means that your runtime is actually 150 times slower than what you would have wanted. And so I leave that as an open question to, usually ceilings don't really matter in anything, but here it gives you, it makes your runtime slower by an e to the epsilon factor roughly. And that's kind of why we picked k, and this experiment was picked in a certain way that was actually beneficial to us, which was this q to the t minus 1 over q minus 1 was exactly that number. So we're just like, let's let k be that, okay? Yeah.
This is the runtime for producing the entire
F tilde.
F tilde.
That's right.
For any of the schemes, if I just wanted to be able, I wanted a data structure where I can just probe to get a single value of F tilde.
Yes.
For a better
Yeah, you can, well,
time, like an
Yes. I think every scheme has that property. Every scheme I've talked about. So, no, wait. Okay, subset selection. Maybe not. Maybe not.
Your scheme has that.
Our scheme has that property. Yes, our scheme does have that property. Yes. Okay.
And I guess
yeah.
actually maybe a related question is if K is very big, you might also want like a heavy hitter style
That's right.
extraction algorithm.
That's right.
I know one of the things that people have proposed in the literature is sort of like there are various, at a cost of just a log K factor, I can, or log whatever factor.
Yeah, log domain size or whatever. Yeah.
Yeah, I can sort of, use prefixes or whatever these
Yeah.
sort of tricks from the streaming literature.
Yeah.
Can one get away without it? Can style guarantees? Can you get that sort of efficiency bump without paying any accuracy?
Yeah, I don't know the actually. In fact, I guess me and Mark and Uri have a paper in this space, and probably other people in this room also. I don't, here we were really obsessed with getting exactly the right utility loss, and like those works, I'm not aware of one that gets exactly the correct constant, and things like that. Right? No, I don't know. I don't know any positive results in that direction. But I mean, that would be good if to get such a thing. Yeah. Oh, okay. And so yeah.
Sorry, I realized we were supposed to be asking.
Oh, okay.
And speaking the right constant, is that 4 is known to be optimal?
Yes, that's right. Yeah, like this expression, 4n e to the epsilon over e to the epsilon minus 1 squared is optimal up to 1 plus little of 1. I mean, we didn't prove that. That was known before us. That was known by the subset selection people. Yi and Barg. Okay. So maybe I'll just say a little bit about like why is our scheme fast? Where does the fast algorithm come from? And the idea is to find a recurrence relation and use dynamic programming. Okay, so it's first time in my life implementing DP, not for a homework problem. But maybe I won't spend. Oh yeah, the other DP.
Was it also your first time implementing a differentially private algorithm?
Oh yes, it was. It was also my first time, for both DPs. So what do we need to do, right? So f tilde of x is this like. You always add the beta for each message. You only add the alpha if it's a preferred message. So, since you always add the beta, there's a beta n there, and then factor out the alpha. So you need to calculate the sum for each x. And now just remember for our scheme, what does it mean to be a preferred message? It means that, so let me write it like this. Let me make a new histogram y, indexed by message space, where y sub u is the number of messages I got equal to u. And then now what I want to do is I want to sum up y sub u for all u that are preferred. Namely, all u such that x dot u is 0 mod q. So I need to compute this sum for all x in the domain simultaneously, and I want to do that quickly. So naively computing that sum for each x, well, I could say, look, for each x, there are k over q, a 1 over q fraction of projective points roughly are orthogonal to me. So there are k over q things to sum there, and there are k values of x. So naively, the runtime would be k squared over q, like quadratic time. But I don't want quadratic time. I want nearly linear time. So how do I do that? So I use dynamic programming. So the basic idea is I say, look, let me define this function f, where f(abz) is the sum of yu over all u such that the prefix of u equals a, and the suffix of u dotted with b is z mod q. Where like the prefix and suffix are disjoined. It's like the first j elements are the prefix and the last t minus j elements are the suffix. Okay? So if I write this fabz thing, then realize that what I actually care about is I care about the sum, for me I care about like the prefix being the empty string, right? So j is 0 basically, and the suffix being everything. So what do I mean? So let's just think about what I'm saying here. So let's ignore that for a second. What I want is the sum of y sub u for all u such that u dot x is 0 mod q. So in other words, z should be 0, b should be x, and the prefix should be the empty prefix so that the suffix is all of u, right? So I basically want to know capital F of null x0 for all x simultaneously. Yeah? Okay, good. And then you realize that capital F satisfies a recurrence relation. You basically kind of build a kind of one more entry at a time. Let me not really go into the details. It's not something super hard, okay? It's a homework. It really is a homework exercise. You could, when you're teaching students DP, they could actually solve this. Okay. What?
If they knew what finite fields were.
Oh, yeah, okay, sure, yes. If they knew what finite fields were. And if you do the DP, you say, look, like, how many values, how many, like, triples ABZ are there? And how much time do you spend per triple? So the time per triple, you can see there's like a sum of over Q things. And then, so there are basically KQT possibilities for ABZ, and each one takes Q time. So your runtime would be KQ squared T. And for your space, if you want to use lower space in your implementation, there's this usual trick where, like, if you have a DP table and one row only depends on the previous row, you can save memory. So if you do that, your space will be KQ. You can even save an additional factor of Q in your time and space by observing something, which is that for any zeta, FABZ is equal to FAB zeta Z zeta. If you just look at the definition of capital F, if you look at the definition of capital F, if I scale B by something and scale Z by the same thing, it still gives me the same thing. So now what I can do is I can basically say, I don't need to fill in the whole table. I only need to fill in the table for B being a canonical vector, okay? Because that implies all the other values they're all implied by that. So that saves a factor of Q in both the memory and the time, and then that's actually what we implemented, okay? So this is a linear space out, and it's actually, okay, so I don't expect you to read this code. The whole point is the code does fit on a slide. It's not super crazy. And maybe it's not obvious because the font is so small, but it's like extremely parallelizable. We didn't actually run it in parallel, but there's an outer loop that has like log k iterations, but everything inside of the outer loop is completely parallelizable. So kind of if you had enough machines, you could run it in log time. Okay. And I also mentioned that there's a trade-off. Let me skip the trade-off. It's basically a hybrid between our mechanism and randomized response. Actually, maybe I can tell you what it is. Okay, why not? So the basic idea is you break up the universe into H blocks of equal size. The local randomizer first reveals its true block using randomized response. And then if it decided to reveal its true block, then inside the true block, it reveals its element inside the block using projective geometry response. And if you analyze this, you get kind of what I promised you. Okay. Okay, I have 15 minutes left, I think. So maybe I'll talk about one more problem that we also designed something for, which is mean estimation in the LDP model again. So it's the same setup, but now let's say that, this is like this federated learning stuff, right? So every device has its data locally and wants to participate in some distributed learning algorithm. So it's computing some, at the end of the day, the server wants to learn some parameter of some ML model, and we're running some distributed gradient descent or something, okay? So I compute gradients locally based on my data, and then, I guess the current iterate of my data, and then now the server wants to compute like the average gradient, and then, and then we keep iterating like this. So a gradient is just a vector, so this is now kind of high-dimensional mean estimation, right? We each have our own vector, and the server wants to compute the average vector. Okay. So D is the number of parameters in my model. Okay, good. So I guess this is what I said already. Yeah, federated learning. Let me skip this. So how do you do it? Okay, this is some citations to people who are actually doing this in the real world. Like maybe you can believe me that people actually do federated learning. Okay, so. Okay, so the second problem today is each device holds a vector, which is a d-dimensional vector, and the mean is then, you know what the mean means? Mean means, yes, okay. And the server wants to estimate the mean, and again, I'll look at like L2 error, okay, so I want small L2 error. So there are protocols already out there. There was this one called PrivUnit of Ducci, Jordan, and Wainwright, and there's another one by Bomek et al., where the expected L2 squared is this expression, d over n times 1 over the min of epsilon epsilon squared. And it's known that this expression is asymptotically optimal, okay, amongst, I think, unbiased estimators, okay. And in fact, similar to the case of subset selection, it's known that like not only is the Bomek et al. Mechanism PrivUnit, not only is it asymptotically optimal up to a constant factor, it is actually the optimal protocol. Okay, meaning if you correctly set the parameters in the mechanism, it is better than any other mechanism. Okay, like greater than it's less than or equal to, no constant factor. Okay, I don't even think there's a 1 plus little o of 1. I think it really is the best mechanism. Okay. So what is the priv unit mechanism? So there are 2 parameters. You have to choose them properly to actually get the optimal mechanism. But let me just tell you what it is. So okay, let's just pretend that all the vectors are on the sphere, okay? D-dimensional sphere. So I'm a device. I have a vector that's on the D-dimensional sphere. I need to send you a message. What am I going to do? It's going to be kind of like randomized response. It feels a little bit like randomized response. So I'll flip a biased coin, and I'll do the following thing. Okay, if the coin says heads, what I'll do is I'll draw a small spherical cap around my vector, and I'll send you a random vector in that cap. If it comes out tails, I'll send you a random vector in the sphere which is not in the cap. Right? So it feels like randomized response. And if you set the cap size correctly, and you set the bias of this coin correctly, it will be epsilon dp, and it will have the optimal utility loss. Okay? The fact that it's the optimal utility loss is what was shown by Hillel, Feldman, and Talwar.
Like the Ducci, Jordan, Wainwright,
Yeah.
that's just like gamma equals 0 or something?
Oh, you mean that's, I don't actually remember what theirs is. Yes. Okay. Okay, why is there room for improvement? Okay, so I told you it's optimal. What's not good about it? So the communication is D. It's at least D. Basically, you're sending a D-dimensional vector as your message, right? This random vector on the sphere. You could improve that communication by doing a pseudo-random kind of thing that you mentioned, Adam, which is, and this is actually one of the things that was proposed by HFT, which is, what if I use a PRG to select, so yeah, I have this spherical cap, and I'm trying to pick a random vector in the cap, right? So what I'll do is, I'll have some pseudo-random way of picking a vector on the sphere, a pseudo-random vector on the sphere, and I'll do rejection sampling. Pick a random seed. Is it in the cap? No, it's not. Pick another random seed, until I get one that's in the cap, and then send the seed for the first time that I get one that's in the cap. Okay? So your communication will be better because you're only sending a seed, but your device runtime will be slower because the probability that a random vector, even a random vector is in the cap is not that high. So if you look at what the parameters end up being, what the surface area of that cap is, basically you blow up your runtime by an e to the epsilon factor if you do that. So can you get both low communication and fast device and server time simultaneously? So there was progress by Chen, Kairuz, and Ozgur. This was 3 years ago, less than 3 years ago. And it uses something called caution representations. Okay, so let me just say a little bit about what that is and what their scheme was. So okay, a tight frame is a collection of vectors, let's say capital N vectors. Think of capital N as being like bigger than D. So they're D-dimensional vectors, but there are like 100D of them or something, okay? Such that for any x, you can look at, basically x L2 norm squared is equal to the sum of ui dot x squared, okay? And this ratio of, how much multiplicatively, how much bigger is n than d is called the redundancy, right? So if it were actually just a basis, n would be d, capital N would be d, but you might have 100D of these vectors. Okay. Good, so okay, one property is if you have a tight frame under that definition, then you can write x as basically as if it were a basis. You can write x as the sum, a linear combination of the ui's of the frame vectors, where the coefficients are just the dot products, like as if it were an orthonormal basis. And I'll say that, okay, so now what do I want out of my tight frame to be good for their scheme? So I want it to be a caution representation. What does that mean? It means that if I write the x in that basis, the energy is well spread, right? So there isn't too much mass on any one coordinate, right? So ideally, if you had a d-dimensional vector, if it were perfectly well spread, every entry in that d-dimensional vector would be magnitude 1 over root d. But of course, there are vectors in d dimensions which don't satisfy that. But the hope is that if you can move to a caution representation where the caution representation of every vector satisfies that. So you want that any vector, once you transform it, do this caution transformation into this tight frame, no entry, none of those coefficients ai are bigger than k over root n times L2 norm of x. Okay, and k is kind of how much worse you are than being perfectly well spread. Capital K is like the quality of the caution representation. It looks like Adam has a question.
Is this the same thing as bounding the length of the UI of the UIs?
Is this the same thing as bounding the length of the UIs? That's your question? I don't think so. I mean, an example of a tight frame is like any basis. The standard basis is a tight frame. But then capital K is terrible, right? Capital K would be like root n, because there are vectors in the standard basis that have all their mass on a single coordinate.
But I mean, like, if the AIs are, like the inner product can always be proportional to the length of the UI, right?
Like
some
if
vector
X is
at-
one of the UIs,
Yes.
then
Like, there'll always be a UI such that, so there'll always be an X that's equal to UI, so.
Wait, let me just think for a
the
second.
difference between squares and like the squared norm and the actual.
Oh. Wait, sorry. Yeah, now I see what you're saying. You're saying, like, what if X is UI, right?
Right.
Like, isn't that the way to maximize the inner product for a given norm of X?
Hold on. Now, yeah, I do feel like
The
I'm.
longest UI and
Why am I?
with that guy.
What you say makes a lot of sense, but somehow. I'm blanking. Let me come back to that because I mean, what you're saying does make sense, but somehow, what you're saying also, I feel. There should be something I can say that will be helpful for this, but I don't know what it is right now. Yeah. Okay. Our mechanism is not going to be this anyway, but anyway. Okay. So, but yes. Okay. So there's a theorem which should fix what you're saying, but I should have a better answer than just invoking some theorem without any proof. Which is that there exist good Gaussian representations, right? So basically, if you pick the redundancy to be any constant bigger than 1, let it be 5 or whatever, you can actually get a Gaussian representation where capital K is a constant. And furthermore, you can compute all these coefficients in nearly linear time. Okay, so this exists, and this is what these people use. So what do CKO do? First they pick a Gaussian representation. They compute a Gaussian representation of X. Okay. And then now all the coefficients are bounded. And then they sample some uniformly random coefficients amongst these. There are capital N of these coefficients. They sample little k of them, where k is something small, only epsilon. This is the dp epsilon. And then they quantize those coefficients by randomized rounding. They either round to minus k over root n or k over root n, okay? Doing like a kind of standard randomized rounding. Okay, so you choose the probabilities such that, the more negative you are, the more likely you are to round to negative k over root n, et cetera. And then now you have k bits, and you send those k bits, using randomized response. Okay, so your bit vector is an element of a domain of size 2 to the k. You use 2 to the k array randomized response to send the bits. And then you kind of, on the server side, do whatever you need to do to unbias everything and get an unbiased estimator. And what they analyzed this, and they showed that the utility loss you get is big O of optimal. So it's this O of d over n min epsilon epsilon squared, but it doesn't get the correct constant factor. Okay, so, and in fact, if you look at their paper, they empirically judge their algorithm, and they compare it to priv unit. Okay, even I can't read this. But I think green is their algorithm, and blue is, I think, priv unit. So the point is, their algorithm was like, even empirically, there was worse error. Okay. So do you really, again, similar story as last time. Like, what if you don't want to sacrifice the optimal utility loss? So our contribution is this. So we come up with something we call proj unit. So our communication is also small. It's epsilon polylog d. Our utility loss is 1 plus little of 1 times opt. And our device runtime is nearly linear in D, which is actually even faster than the CKO, than the Gaussian representation thing, which was d log squared D. And our server time is also nearly linear in N and nearly linear in D. So it's kind of up to these log factors in the communication and the server time, or up to the log factors in communication and runtime, it's kind of the best you would hope to get. And bonus is that our algorithm is pretty simple, okay? And here's the mechanism. Here's what the client does, and here's what the server does. And in fact, there's going to be a slight issue with this that I'll fix in a second. You draw a kind of JL. Okay, I work on JL, so I had to somehow inject JL somewhere. So you pick a kind of random JL type matrix, like dimensionality, like Johnson and Strauss kind of matrix, pi, which preserves norms with high probability. On the device side, you compute x tilde, which is pi x, okay? And then you normalize it, and then you apply priv unit to that. and then you send, you send the output of priv unit in this lower dimensional space. So u hat is actually, u is a k-dimensional vector, u hat is a k-dimensional vector, where k is something that's not d, it's much less than d. And you send that together with the C that was used to generate the JL matrix, pi. And then on the server side, you just basically do pi transposes, okay? And then sum it up. Okay, so that's it. For speed, the JL matrix we use is this kind of fast Johnson-Linen-Strauss transform of Ilon and Chazelle or similar things. And again, we have to generate it pseudo-randomly and send the seed to save on communication. And then, this is our kind of our theorem that the error is 1 plus little o of 1 times the error of priv unit, which is opt, plus there's some additive bias, which is little o of 1. There are two things that are not ideal here. One is that there is this additive bias term, which maybe I don't want that. And the other thing is the server runtime is slow because if you look at what the server does, this is basically computing pi I transpose ui takes like d time or d log d time or something like that, right? Think of like pi as the transpose of a FFT matrix, of the DFT or something. So you can apply pi transpose in d log d time, but then there are n of them, so you have to sum up n of them, so it's like nd time. So that's nd. That's not, but that's that's worse than what I wrote up in the box. I wrote n polylog d, not nd, right? So you can actually improve that, and okay, you can debias it. Okay, I'm running out of time, so I'm going to say you can debias it by slightly changing the mechanism. What about the runtime? So to fix the runtime, kind of one thing you could do, wishful thinking, is what if every device just uses the same matrix pi, right? Then you don't need to apply pi n times. You can just sum up all the UI hats and then apply pi transpose at the end, and then you would have a fast thing. It turns out if you analyze the variance from that, it's not good enough. So we do something else that, surprise, works. Okay, who knows why it works? It just did. So here's what we do instead. We pick capital G different capital G different Ilon-Chazelle type of transforms. And then each device uses local randomness to select a random fast JL transform. And then it sends the output as before using that fast JL transform. And it also tells the server which JL transform it used. And then the server does kind of what you would expect. It groups the messages by whoever used the same transform. It sums them up. Then it applies the transpose of that transform. And then it adds them all up at the end. And you can show that the effect on the mean squared error is small. It's 1 plus little o of 1. If you pick capital G, the number of transforms to be something like n over d. And then the overall runtime is, now there are G groups, and each one you have to do d log d. So basically, G is n over d, the d's cancel, and you get something that's nearly linear. Okay, so that's basically it. And I think we did some experiments. We also did some experiments where we actually tried to use this inside of a learning algorithm on MNIST to see what is the loss in the downstream accuracy for the model you learn. And I think I'm out of time and I'm out of slides, so I'm happy to answer questions. Okay.
Yeah. So I hope the answer is not too simple, but a lot of the mechanisms that you talked about were of the form flip a coin, if heads, sample uniformly from this set, if tails, sample uniformly from this other set. Is there a simple reason?
So I know for mean estimation, so remember I told you that there's this kind of lower bound, I guess, shown by HFT that priv unit is the optimal mechanism. And kind of one of the first things they did was prove some kind of structural lemma where they said any optimal mechanism can be converted into any mechanism can be converted into a new mechanism that's only at least as good, that basically has this 2 probability property. So yeah, at least for mean estimation, without loss of generality, optimal protocols look like that. So you can focus just on those.
question about the histogram, the first part of the talk.
Okay, yeah.
So, one problem that smells like the combination of the two parts of the talk is like estimating means if your vectors are in the simplex.
Yeah, then that's right. It is, you mean, like, you're saying that histogram estimation is a special case of mean estimation where all the vectors are standard basis vectors, right?
Right.
Yeah, okay.
Right. Now, but suppose each person's input is not a standard basis vector, but a distribution over basis vectors. Like,
okay, sure,
it's a L1 bounded vector.
Yeah.
When epsilon is small, like less than 1, it turns out there's sort of basically no, like one approach is you say, well, I have a distribution, I'm just going to sample from it to get like an input, and I'm going to feed that input into a histogram computation. And when epsilon is small, that doesn't cost you anything because the error from sampling is fine. Like,
okay.
But for epsilon significantly larger than 1, that's no longer true.
Okay.
I mean, it depends how big it is, obviously, but like, and so the question is, I guess, do you know if people have looked at, like, in that regime, what should you be doing? Like, it seems like the protocols are very tailored to this sort of sparse vector input, where you just have one item.
Yeah. You mean for histogram?
Yeah, for histogram,
yeah.
right? Like, and so it's like unclear whether or not, to me, whether or not one could adapt those algorithms to solve like L1 mean estimation, which might be useful in lots of settings where I want to split my vote among many things. Or,
yes. So just to make sure, I'm going to repeat some of it just to make sure I'm absorbing or understanding correctly. So, like the second part of the talk, for example, was mean estimation, but it was assuming that the vectors were in the L2 ball. But you're saying, like, if I assume they're in the L1 ball instead, what would an optimal protocol look like when epsilon is not small, right? And I don't know the answer to that. I don't know if someone else knows the answer, maybe, but I don't know. Yeah.
Other questions? Further questions? All right. Let's thank Jelani. And we'll take.
To be
We should let Jayshree get through the talk really fast so that you can finish your thesis and submit it. But Jayshree, for the moment, is still a student at Harvard, and like many great differential privacy researchers before her, is a graduate of Henry Gunn High School in Palo Alto. And is going to talk to us about data perceptions and practices.
Great. Thank you so much. Awesome. So we've heard some great theory talks. So this will be more of a talk around social factors, around deployments of differential privacy, which I know that many people in the room are interested in or involved in different ways. So, and this is based on work with Dana Boyd, Sophia Song, Audrey Hake, Tanya Slater, and Salil Wadan. Okay, so as we've seen differential privacy move from theory to practice, we've seen on the one hand, a growing consensus that differential privacy is the gold standard for privacy protection in certain settings. And it's beneficial for data sharing and privacy across government, industry, and academia. At the same time, these deployments have also shown tensions between the ways in which we formalize privacy compared to the social and contextual factors that are different in each of these deployments. And to give you a sense of some of the social and technical factors that we might be thinking about in these different deployments, They range from having algorithms and analyses that cater to existing practices around data and purposes of data use, to communication efforts that are attuned to perceptions around data in these different contexts. And I think we focused mostly on the algorithm and analytical side in the DP community, but I think there's growing interest in looking at all of these other factors that interact with the wonderful work that's being done in the theory space. So in particular in this talk, I want to call attention to how the adoption of differential privacy is shaped by perceptions and practices around data, but it also creates opportunities for creating new perceptions and practices that align better with our modern understandings of privacy risks. And what I hope to illuminate is that being more attuned to these social factors around how data is actually seen and used in these different settings can help us overcome what we might feel are sometimes irrational oppositions to differential privacy, for example, in the case of the US Census, which I'll talk about, especially for these settings in which differential privacy seems particularly well-suited and beneficial for the goals of both privacy and open access to data. So in this talk, I'm going to explore some of these social factors through two studies. So the first is looking at the controversy around the use of differential privacy in the 2020 US Census, to understand how perceptions around data shaped the response to differential privacy by different data user communities. And then the second will, in more detail, look at tensions between differential privacy and the practices of data science, and give us some opportunities to look at ways in which we can build tools, education, and guidance that can bridge these gaps between theory and practice. And I'll conclude with a few thoughts on how we can sort of better foreground social factors, learning from these deployments of the past decade, to better anticipate challenges around deploying differential privacy, and also use our perspectives from theory and formal privacy to spark conversations around how we can more responsibly orient ourselves towards data in these different settings. Okay, so beginning with the story around differential privacy in the census, which of course many people in the room were more involved with, I'll start by giving some background on the US Census. So the American Constitution designates the census as our democracy's statistical and political data infrastructure. So Article 1, Section 2 mandates an actual enumeration of the population every 10 years, and then this is used to allocate funding and political representation. And so there's no surprise that every 10 years we see fresh controversies around the validity of the numbers and how they're used to allocate money and representation. I'm going to focus on the controversy in 2020, specifically the one around differential privacy. Of course, there were a lot of other things happening in 2020. But I want to focus on how the adoption of differential privacy kind of revealed differing perceptions and practices around census data. A brief look at the history of disclosure avoidance for the census. So in 1850 was the first time when the census decided, maybe let's not post the responses of the census publicly in the town square. Maybe people would like that. And then moving on to suppressing small area data and whole table suppression. In the 1990s is when they started actually introducing controlled perturbation through swapping and blank and impute. And these heuristic methods seemed reasonable, but of course, as we know, the Bureau was able to run an attack that re-identified a large portion of the individuals in their published 2010 decennial data, and recent work has built on these attacks. And so it seemed like a natural progression to move in 2020 to differential privacy to kind of defend against these modern challenges. Yeah?
Were any of these sort of evolutions motivated by a specific incident that you read about?
I don't know too much about that. I know that there have been concerns about privacy in different ways. For example, the way in which census data was used around Japanese internment, but that only came out in the early 2000s. So it wasn't maybe directly tied to the methods that were used at the time. Cool. Great, so while many saw this as a natural progression of modernizing disclosure avoidance and a possibility to adopt trustworthy protections, also providing transparency around how the noise was added. So there's a lot of optimism around this from computer scientists as well as people within the Bureau. But then many stakeholders, media outlets, and members of the public actually saw this as a potential corruption of critical data products. And I think many people in our community were trying to figure out why there was such an incensed reaction to the adoption of differential privacy when it was pretty similar in many ways to what was being done before. And then, of course, to remedy this, Census Bureau scientists and then computer scientists tried to engage with these data user communities, spending a lot of time to try to explain what was actually being adopted with differential privacy, how this worked, and also releasing from the Census Bureau demonstration data products for people to play with. And the goal was that through being more transparent with these technical means, you could get people to understand and accept this new disclosure avoidance system. But instead of bridging the gaps, these efforts only serve to widen the rifts between those who wanted differential privacy and those who saw this as a corruption of data products. And so the goals of our work were first to map perspectives around differential privacy in the census. There are a lot of different stakeholder communities and a lot of different narratives around this. And then second, our hypothesis was that given how intense the reaction was, that maybe this was not just a dispute about the technical details around differential privacy or about privacy itself. So we wanted to go beyond sort of the well-documented technical debates to investigate whether there were non-technical contours of this controversy at a deeper level. And third, we wanted to provide some theoretical framing to help make sense of this controversy and its implications for us, maybe deploying differential privacy in different settings, but also it's a great case study of modernization of critical infrastructure for political use. So between myself and my collaborator Dana, we collected lots of qualitative data through public events and materials, but also through fieldwork and observations. We drew on literature from science and technology studies and sociology of statistics for our theoretical framing, which I won't talk about too much today, but I'm happy to answer any questions about that. Okay, to start mapping some perspectives around differential privacy, first, many privacy advocates viewed the change to differential privacy as essential, even if they had concerns about how it was being done. So the Census Bureau really relies on having privacy now to create trust in data and create trust in the census for decades that will help response rates stay beneficial enough to have good data. So even though privacy and accuracy may have to be a trade-off in the short term, privacy now leads to better data and accuracy later. And of course, computer scientists and statisticians appreciated the transparency that was now possible with differential privacy compared to previous sources of noise infusion, where you weren't able to release the methods in which the noise was added. But with differential privacy, the Bureau could release these demonstration data products, code, et cetera, without affecting the privacy guarantees. So the biggest challenge and controversy around this came in March of 2021 when the state of Alabama sued the US Department of Commerce, which contains the Census Bureau, for its use of differential privacy, supported by many other states. And so this was kind of the climax of a long stage of increased controversy from data users and the public and media outlets as well about how differential privacy would affect the data products that were used for many, many different cases. So this court case was dismissed, but it highlighted a key split in how the census versus its critics thought about differential privacy. So Bureau scientists believed that the noise due to differential privacy was often negligible compared to other sources of uncertainty in the data. And they saw this as a beneficial thing. We're not really affecting the inferences that can be drawn using census data. On the other hand, data users felt that the noise due to differential privacy and other sources of uncertainty, now that they were being talked about, were suddenly highlighted, and they were being asked to think about all of these sources of error in a way that they hadn't before. The Bureau thought that transparency was important for trust in data and downstream inferences, but many data users saw this technical transparency as revealing the corruption of these data products, not just through differential privacy, but over many decades, which the Bureau had not talked about in that way before. So once we mapped parts of the controversy, we had many questions that I think people in this community also had. So first, what do the communication challenges reveal about the deeper perceptions and practices around census data? Why did efforts to bridge the divides only cause further rifts? And what can we learn about deploying differential privacy for public use in similar settings beyond this case? A quick overview of the findings. We found that differential privacy exposed and widened what we call epistemic disconnects around census data. So disconnects in how people viewed knowledge production via census data, how the data is used for the myriad of use cases, from policy to funding to just understanding our society. And we show how communication around differential privacy actually widened this disconnect. And the next few slides, I'll become more concrete about what these disconnects actually were. Second, we define a theoretical concept of a statistical imaginary that I think is helpful to capture how these perceptions around data related to the larger political visions around census data. Okay, so I mentioned epistemic disconnects, and so here I'll be more concrete as promised. So we found different conceptions around, particularly around accuracy, granularity, and privacy of census data. And the Census Bureau calls these three attributes the holy trinity of trade-offs. So you can't have all three at once, and you have to manage the trade-off between the three. So in terms of accuracy, we saw that many traditional data users, longtime stakeholders of census data, considered the data to be the best possible enumeration. That's a phrase that kept coming up, and something that could be used as is across many applications downstream. Of course, on the differential privacy side, many people who aligned with this highlighted the uncertainty of many forms that were already existing in census data and saw these as estimates that could be used for specific purposes rather than could just be taken out of context and used broadly downstream. Second, in terms of granularity, many traditional data users were interested in the data for fine-grained accounting on a small area or individual level. And this often looked like balancing births and deaths on two sides of a spreadsheet. That's an example that kept coming up. And so they wanted the census data to be granular enough to be able to use it for things like that. And then on the other side, many advocates of differential privacy felt that the data should only be used to create aggregate inferences on a population level. And when we talk about inference, then we're naturally able to talk about uncertainty. And then finally, for privacy, many data users felt that the attributes in the decennial census were minimally sensitive, information that could be found elsewhere, while many advocates emphasized that, of course, we can't predict what is sensitive a priori if we want to be mindful of all possible future attacks, which the other side felt like a very conservative way of dealing with risk, but totally makes sense when we think about it in the differential privacy context. So these disconnects we find are not just different perceptions around data. They're embedded within ways of working with data and are tied to specific visions on how census data upholds political arrangements. So to capture this concept, we define statistical imaginaries as infrastructural visions of political arrangements upheld by networks of people and data practices. And so this is a very science and technology studies kind of term, and builds on a lot of literature in that space, but I think it's helpful for capturing exactly what was at stake with census data. In particular, we can actually think about what is the statistical imaginary that we were working with here with traditional data users. And what it came down to often was a fair republic rooted in this notion of best possible decennial enumeration. And that goes back to the constitutional understanding of the census as an actual enumeration to allocate political representation and funding. So this is very central to the infrastructure itself. And now when we're able to articulate this kind of imaginary that ties together how people think about data, the practices around data with the broader political understanding of that data, we're able to understand where people are doing work to make this imaginary exist, even with our modern understanding of data as not being a actual enumeration of people. And so I'll make this more concrete by talking about two specific data practices and what we call statistical illusions in our paper that we think uphold this imaginary of the census data as this actual enumeration. So the first one is a statistical illusion of ground truth. So a narrative around census data, published census data being able to be thought of and used as ground truth. And the second one is microdata, which I'll come back to. So like I said, the first illusion is that published decennial census data can be thought of as ground truth. And this narrative is upheld by stakeholders as well as the Census Bureau itself. So here's an example diagram from the Bureau that shows the different stages of conducting a census. And so it talks about targeting hard-to-reach communities, motivating people to self-respond, and then following up with non-response populations. And then the last step is just tabulating data and releasing census results. But in fact, there's a lot more that goes into this last step, and maybe that's actually the biggest step of the census project. The Bureau does a significant amount of work to repair, edit, and process the data towards creating what seems like a complete and accurate count of the population. And then, of course, that involves imputation, deduplication, and other statistical methods. And then noise infusion is added on top of that. So previously, the Bureau did not release any sort of metrics about error in all of these forms of repairing or editing the data, nor could they release information about the noise infusion itself. And so that whole side of the data processing pipeline was kind of obscured from the point of data users. And so now what happened when we are suddenly able to be transparent about differential privacy and asking people to evaluate the data quality of demonstration data products is that they conform to this statistical illusion that had been in place for many years. So they used the 2010 published data as their ground truth when comparing to the 2020 demonstration products, without accounting for all the different sources of noise that existed in the 2010 data. And so this led to several apples to oranges comparisons, which made people within government very confused as to why people were using the data in this way. And stakeholders, on the other hand, when they were told that they should account for all of this noise in the data, were very upset to hear that they were now asked to be thinking about this data in a very different way than they had before. So this illusion of ground truth was kind of incompatible with actually allowing for meaningful evaluations of the data by stakeholders. And in the process of explaining differential privacy, this illusion suddenly became visible to the public. Okay, and the second illusion was the format of the data released by the census. So with differential privacy or other forms of noise infusion, you would add noise that could produce negative people or potentially fractional counts. But the Bureau decided to post-process these counts into microdata, so counts of individual people, even though many of these people are algorithmically imputed and the data is not precise down to the individual level. But this desire to represent the data in this microdata format with things that seem like actual people comes from, again, the constitutional language of an actual enumeration. And it seems like an objective and neutral way to represent the data, but it actually projects a lot more certainty about the data than we actually have with this kind of census data. So, and it hides how, in many ways, the data produced is actually synthetic to some extent. So the decision to maintain this illusion through post-processing again hindered the ability of different parts of the community to evaluate the error induced by noise infusion. And so it made it hard for differential privacy folks to support the system without having access to the raw noisy counts, and there were many requests to release these noisy measurement files. Okay, so that's just a quick glimpse of two data practices, or statistical illusions, that uphold these narratives around data, and that were completely in conflict with how we think about data with differential privacy. And so what we find is that, on the one hand, the Bureau is trying to maintain some of these illusions while also trying to modernize how we think about disclosure avoidance. And those were completely conflicting imaginaries. And the more they tried to communicate about differential privacy, the more they were shattering the illusions that they had previously upheld. And so although this controversy seems at first to be about this like new technical system, we found that much of the debate and the intensity around the debate stemmed from these deeper epistemic disconnects. So one thing to take away is that communication via transparency, such as releasing code or open source or demonstration data products, requires having a shared understanding of what that data is, how it's made, and how it will be used. So to summarize kind of what I just said, we have to kind of look at the statistical imaginaries around the census to understand the deployment and the debates around this deployment. And integrating differential privacy in this setting as well as other settings, definitely requires technical tools, communication, but it also requires us rethinking and reshaping perceptions and practices around data so that they match up with how we think about data with differential privacy. And so this case study brings up some interesting questions, I think, that might be helpful for deploying differential privacy in similar settings, particularly ones that are highly contested. So first, we want to examine what are the existing statistical imaginaries in that context, and what functions do they serve? So maybe from the point of view of the differential privacy community, it doesn't make sense at all to think about census data as an actual enumeration. But that is a choice that was made even after our understandings of data had modernized, possibly for many reasons around trust and legitimacy and stability of the infrastructure. When we open up the uncertainty for critique and for people to evaluate, especially in such a highly contested, politicized data infrastructure, a lot of bad things might happen. And so we have to kind of grapple with what differential privacy is asking people to do in that context when they start talking about uncertainty. So we might think about how differential privacy would upend these imaginaries, and maybe some of our work in deploying differential privacy is not just with the privacy protections, but also rebuilding the broader understandings of and perceptions and practices around data. I think that one thing to remain optimistic about is that deploying differential privacy gives us an opportunity to reshape these perceptions and practices, even beyond our goals of privacy. So here are two really nice examples of work that evaluate the impact of differential privacy on how census data is used for redistricting and funding formulas. But instead of just looking at how noise addition changes these practices, they also highlight the much greater sources of noise in the data and how we should be rethinking our treatment of census data as a pure enumeration in order to provide more fair and robust policies in both contexts. So it's an opportunity to have a conversation around how can we better design funding formulas so that they're not so sensitive to changes in the data, or how can we rethink our voting rights practices so that they're not dependent on a single person, single vote. Okay, great. I think I will pause there for a second to see if there are any questions before I move on to the second part of the talk. Yeah.
I'm not sure if I have the right way of asking this, but you sort of outlined this idea that people have these sort of illusions about the data that were kind of shattered by switching to DP, and also by the way this communication happened. I guess I'm curious, sort of based on your experience or the insights of kind of the field of STS, would one predict that this is a problem that's transient or sort of permanent? Is it that once a technology is deployed and creates this type of reaction, kind of there's no recovery, or is it just that eventually people's illusions around the data will change and this will seem like a quaint controversy in hindsight?
That's a good question. I think eventually, and we're already seeing that people are starting to accept differential privacy and starting to accept the way that we're talking about noise in data. But I think as people who are designing the technology that kind of causes these rifts, we both have the responsibility and the opportunity to shape how people come to a consensus around that in the future. So does that actually look like downstream, more responsible uses of data downstream, or does that look like people in the first level kind of figuring out how to work with differential privacy, but still in the many downstream uses of the data, the uncertainty is still not being accounted for in the right ways. And I think the insight from STS is that this is not a deterministic outcome. So how this plays out, I mean, it will probably stabilize and play out in different ways, but that really depends on the people in the conversation shaping how the data is perceived in different ways.
I guess this is a somewhat related question. Does this perspective suggest ways one should try to address these disconnects? And I'll give you a specific example. I was at a workshop last week involving, among other people, lots of economists, and somehow this idea that synthetic data generated by the census shouldn't be taken at face value as even once you've explained that there's noise being added, the conversation really centered around okay, for which set of analyses can we, the most technically sophisticated version of it was, fine, tell me what sets of analyses, the sets of analyses for which I can just use this data, the synthetic data, as if it were real. As opposed to what's the most, useful thing I can do with this this object that was generated. Right? And so, it struck me at this workshop, and I tried to make this point to people when I could, that just the conceptual framework hadn't actually shifted that far. And so, these insights tell us anything about how as a collection of communities, we might go about, shifting the framework and getting people to think differently about stuff?
That's a really good example, I think, of what we were just talking about. Maybe it shifts the practices of the first set of users, but even then, people are reluctant to change completely how they work with data, and obviously, it's easier to not have to think about uncertainty in different ways. So I think it really comes down to being proactive about shifting that on sort of every level, from how we teach data science, how we teach economics, and creating sort of examples where we can be you might think you can use the data in this way, but you will clearly be wrong, and this is why, and the effects of that in sort of more high stakes situations where people can kind of understand better that it's not just a nice thing to do to take the uncertainty into account, but it actually can have major consequences if they're not doing so. Especially with differential privacy, maybe that the stakes are higher in terms of what can go wrong if that noise is not taken into account.
Have you been looking also into, so you mentioned the statistical illusions or falsehoods, about privacy illusions, because this also are part of the way people think about the census and about privacy. Let me give a few examples like that. Either you have privacy in the data or you don't. It's not something that is graded. The fact that composition is important is kind of unknown to many people and so on. Have you seen this kind of disconnect between these illusions and what we know scientifically now, and whether these actually are also manifested in the way people were discussing the census data?
Yeah, I love the reference to privacy illusions. I think that it's very similar in that we have to kind of think about where those illusions are coming from and who they might benefit. So, I mean, I think this myth around like you either have privacy or you don't, and then it's very easy to say, well, of course we don't. And so it makes it very hard for people to actually motivate themselves to care about doing anything in the face of this like binary notion of you have it or you don't. So I think that the conversations around census are maybe more nuanced in terms of privacy than maybe we see in industry settings, because it's not just a technical thing that we're implementing, but there's also like legal and moral and like business obligations of the census to care about privacy. But then you very much see, even if the Census Bureau itself is trying to work through these illusions, the data users themselves are kind of like, we've already been told so much that we shouldn't care about privacy because we don't have it, and so it's not worth protecting in the census because we don't have privacy anywhere else anyways, and so we should just be caring about data accuracy. But I think these myths kind of tie together in terms of the greater kind of political visions around what people are able to do if they have this myth or they don't. I guess I'll also add that I think, and your work on this, obviously, I think the legal understandings around privacy are starting to change. And I think a lot of the kind of need to grasp onto these, both the statistical illusions and the privacy illusions, are kind of an operational thing in terms of having to conform with the ways in which the law understands privacy, or the law understands uncertainty in census data, which is to say, not at all. So, so I think it's kind of changing the landscape in all of these different ways that will actually create different perceptions. Okay, great. I will move on to the second part of the talk, which is looking sort of beyond this case study of the census to understand more broadly about the practices of data science and how they're kind of already in tension with differential privacy in many ways. So this study aimed to investigate the utility of differential privacy for facilitating privacy-preserving data science that is accessible to non-expert data practitioners. And we do so through a qualitative study observing participants use an interface called DP Creator, which is powered by the OpenDP open source software library. And so much of the work, I think, in the census case is looking at data subjects and how people use DP software. But it's also really important to look at the challenges of using differential privacy from the perspective of data practitioners themselves, so data providers and data analysts. And I think this is an increasing point of study in recent years. So data providers collect data from data subjects, and in the data sharing framework, they would upload this data to an archive, such as Dataverse, to allow it to be accessed by other researchers and the public. And analysts typically have to go through a lengthy and costly process to apply for raw access to the data, but with the differential privacy interface, they can access the statistics that are released by the data provider as a default, or query the interface for additional statistics. So I'm going to talk a little bit in depth about the process for data providers and then move on to data analysts to see kind of how this, an interface like this would work in practice. So the interface we used is called DP Creator. It aims to make it easier for non-experts in differential privacy to reap the benefits of data sharing, such as broader access to data insights, easier exploration of restricted data sets, and replication of scientific studies. And here's a display of sort of the provider landing page, which prompts users to go through these different steps to upload and release statistics. So in this work, we consider what challenges do data practitioners face when using differential privacy to share or analyze sensitive data sets? What do they perceive to be the utility of differential privacy for the different use cases that I talked about before? And then what are the implications for privacy-preserving data science in terms of ethics, epistemic, and research questions? To explore these questions, we conducted semi-structured interviews with 19 data practitioners who are non-experts in differential privacy, but were experienced in sharing and analyzing data in the context of research data repositories. We sorted them into the roles of data provider or data analyst, and then we observed as they talked out loud as they used the DP Creator prototype to share and release statistics. Our analysis was a thematic analysis mapped onto the data science workflow, which I'll talk about in a later slide, to try to identify areas of tension and further research to bridge the gaps between differential privacy and current practices of data science. So I'm going to go through some of the challenges that we found for data practitioners using differential privacy, starting with data providers. So the first finding is that they had to make many new choices when using DP Creator compared to their usual processes of just uploading data, and they had trouble understanding the reasoning behind or implications of making these choices. And we often talk about the choice of setting the privacy loss parameter, especially in deployments, as a policy choice, but there are lots of other decisions that data providers have to make. So making sure the data set is suitable for differential privacy, that it is based on individual level data, setting metadata parameters such as ranges and categories for different variables so that you can apply differentially private algorithms that require these. And then, of course, allocating privacy loss budget across different statistics as well as different analysts who you want to give access to. And I'll quickly illustrate what some of these choices look like in the interface. So the first step, once the provider uploads the data set, they're asked to validate that the data set is suitable for differential privacy so that it depends on private information of data subjects and each individual appears in only one row. Next, the data provider is asked to estimate the data security level of the data set, and here it's according to Harvard information security guidelines, but this could be institution-specific guidelines, which then the tool converts to privacy loss parameters epsilon and delta. And so we don't have, of course, a consensus on exactly how to translate between data providers' understandings of data security level to these specific privacy loss parameters, but these are kind of a reasonable way of doing that. And then the data provider is asked to provide info about how the data set was sampled. If it was a secret and simple random sample from a larger population, this could be used to amplify the privacy guarantee. Next, they're asked to correct the inferred variable type and input metadata parameters, which are required for many of the differentially private algorithms. And they're told that these metadata parameters should not be taken straight from the data set, but that they should be sort of reasonable information about the type of the variable based on domain knowledge. So inputting 0 to 100 or 110 for ages of humans, but not inputting the exact min and max ages from the data set. And then from the analyst side, they can actually look at what the depositor or the provider has set for these metadata parameters and adjust these based on their goals around bias and variance of the algorithms that they would like to deploy. And then finally, for both providers and analysts, they can create statistics using the tool. The tool will by default split the privacy loss budget evenly across these statistics and show the error due to privacy noise, but this can be adjusted by the user. Okay, so back to the challenges. So data providers not only had trouble understanding why they had to make a lot of these choices, but they also struggled with assuming these kinds of new risks and responsibilities. Many people said that these choices seemed to require lots of trust in the tool, and even though the code was available open source, they felt that this was a very kind of black boxy way to create statistics. Some non-expert users even said that they were afraid to harm their careers if they messed up, and so they felt that you would actually have to be educated in differential privacy to feel confident, even though the tool was designed for non-experts. Now, data analysts had less of these kinds of choices about the data set to make, but they faced challenges in conducting the analysis without access to the raw data. So many participants found it hard to do analysis without checking small things in the data, such as how missing valuables were coded, or distributions of variables. And they also had a hard time interpreting error guarantees, such as the error due to privacy here on a histogram bin without having additional contextualizing statistics, such as the number of total observations, which they might have to spend additional privacy loss budget to release. And then across the board, all the analysts were very worried about being able to do any sort of exploratory analysis under the constraints of this finite privacy loss budget. And so they were worried that they would screw up their analysis by making the wrong choices early on, and they were unsure how to allocate the budget across multiple statistics. So overall, we found that differential privacy significantly changes every step of the data science workflow. Even maybe in small ways from a theorist's perspective, but from the perspective of the practitioner, this really made it hard for them to trust that they were experienced enough to actually do this process. So this is a workflow of data science by Philip Guo, which outlines 4 stages of data science. So preparation, such as data cleaning, analysis, such as running scripts, reflection, such as making comparisons, and then dissemination through writing reports and such. So now the participants in our study, in the role of data analysts in particular, also went through these different stages as they were using the DP Creator prototype. And I'll map some of the challenges that they faced onto this workflow. So first, in the prep stage, they found it hard to understand data and check assumptions through the interface, as I said, without having access to the raw data. In the analysis stage, they were not sure why or how to adjust these metadata parameters to satisfy their goals around bias and variance of the statistics, and also felt daunted by this finite privacy loss budget. In the reflection stage, they found it hard to interpret accuracy guarantees, as I mentioned, without full context of the data. They also worried about how they would debug the outputs or trust the findings without having access to the raw data. Finally, in the dissemination stage, they were unsure how they would sort of cite or explain these results to those who are not familiar with differential privacy. And they were also worried how they or others would do replication studies, given that the outputs were now additionally noisy. Kind of going back to the previous talk, I think replication is particularly challenging, even with a tool like this, because many studies are not able to fully publish every step that they did when they were working with data. And without that, it's very, very hard to replicate. So this leads us to a core insight again from science and technology studies, which is to think about technology as not just products or definitions, but as practices. And so we should think about differential privacy not just as a definition, but a set of norms and practices that we have to socialize data users around. If we take seriously the constraints of differential privacy, this indicates that a new set of workflows have to be adapted to satisfy the privacy guarantees of differential privacy. And so if we kind of fix this technical definition and then say that we're going to reconfigure the social practices, that comes with different ethical and epistemic implications. So what are the ethics of doing this? How would this change how data is used for knowledge production when constrained by these different assumptions of differential privacy? And then what are some suggestions to kind of bridge these gaps with design and research?
What do you mean by the ethics of socializing data practitioners?
Yeah, I'll probably talk about that in the next slide. But kind of to answer that question briefly, this requires training data practitioners to adopt new ways of working with data, and also kind of takes away their agency and judgment in many ways of being responsible for the process of the data, while assuming kind of these new risks around potentially compromising the privacy guarantees if they do something wrong without knowing it. So that's kind of, it's kind of not the big ethical dilemma that maybe you're thinking of, but kind of how does this change their like responsibilities and risks around doing data science? So first, on the point of data access, many of our participants were very enthusiastic that this kind of tool would offer wider access of data to the public, or even within their own research organizations between people who had access to the raw data versus others who just needed to understand the insights. But as I mentioned, this kind of dream of being able to do kind of robust exploratory analysis, I think there's a ways to go before data analysts feel confident actually being able to explore the data under these constraints. Second is around expertise, and this is kind of what I was mentioning. Many of our participants came back to this idea of having to work with the data through this black box, and so they felt like they were just, their own understanding and judgment of the data was constrained in many ways. This also, kind of going back to what we mean by like ethics of socializing data users, is that this means we have to articulate a new kind of vision around what is ethical data science. Many of our participants thought that ethical data science was working really hands-on with the data so that you know it super well and you're not making assumptions or inferences that are not actually founded by the potential that the data could provide. And you're actually being cognizant of the limitations. But now this is kind of a new articulation of ethical data science of being removed from the process of working very hands-on with the data and working with it through this black box. So those are kind of competing visions in some ways. And then finally around trust and safety. So again, working through this interface provides protection against privacy attacks and overfitting, but many of our participants were worried about the implications for trust in terms of debugging the pipeline, validating the outputs, replicating results, and communicating findings. So I'll briefly end this part with some suggestions for design and research around differential privacy tools. So first is better guidance around setting parameters and making decisions. As I said, many policy conversations focused on just how to set a few of these parameters, but there's kind of in every step of the data science workflow, the data provider or the data analyst is having to make different judgments around how to work with data in this new way, and so we need better guidance around that. Second, practitioners would benefit from having a database of information on how these decisions are made across different deployments, which is proposed by Dork et al. With the Epsilon registry to guide parameter settings, and I think this will be extremely helpful for people feeling more confident around making these decisions. Second, it's important to design workflows around trust and safety, not just for the data subjects, but also for the practitioners who are responsible for the data subject's privacy. So we need to focus on algorithms and metrics that rely minimally on making assumptions about the data, as that's really hard to do under these new constraints. And I think there are many easy ways to provide guide rails for practitioners through these kind of like simple add-ons to tools. We also, I guess, need clarity on the responsibility of data practitioners if something goes wrong. So as I said, many people were worried about the liability that they held in doing this process. Finally, I think what would really help around sort of trust and safety, but also exploration, is having better features around contextualizing the data. So this might look like even a very rough baseline synthetic data generation plus visualizations provided by the tool for checking assumptions about the data. But this study also highlighted the need for much more detailed data set annotation on the part of data providers. And so we recommend that they provide detailed code books and default releases of these statistics that would help contextualize the other findings, such as number of observations, number of missing values, distributions of key variables. And I think an interesting thing about this recommendation is that this works really well with this recent push towards data set annotation for the purposes of mitigating bias in in data sets as well as models. So the data sheets for data sets work and model cards in the fact space. And so these measures are also really important for conducting analyses under privacy constraints. So the takeaways of this work are that differential privacy introduced these new challenges into every step of the workflow. And that makes, it is beneficial for wider access to the public, but it does pose challenges for exploratory analysis and replication of scientific studies without having tools to sort of bridge those gaps. Working with these new social practices around differential privacy requires concerted efforts around training, expertise, and governance, in addition to developing usable tools. Okay, I guess I'm close to time. So I will end by summarizing some of the takeaways from this work in terms of how we can think about foregrounding social factors as a way to create smoother uptake of differential privacy in practice. So when thinking about deployments, what both of the studies I talked about today indicate that it's important to pay attention to data perceptions and data practices. So in particular, data perceptions might look like how is data understood to be collected and created in that particular context? How is uncertainty within the data made visible or invisible by the different actors around the data? And then data practices, what are the norms and workflows around sharing and analyzing data, and for what purposes are these data used? And I think it's important to point out that these perceptions and practices should also be put into the broader sociopolitical context. So why do these perceptions and practices exist in the first place, and what might happen when we break those assumptions? And I'll end by reiterating that I think deploying differential privacy successfully may require understanding these new perceptions and practices, but also actively reshaping them. And I think by doing so, we'll be better able to anticipate the challenges around adoption of differential privacy in these different contexts, and to influence the broader ways in which people work with data, beyond just privacy goals, but in terms of responsible understandings of data across the whole data pipeline. Okay, with that conclude. Looking forward to questions.
Further questions for Jayshree?
Lydia?
So the people who are using DP Creator, could they not see the number of rows, the number of, sorry, the size of the data set, or the bounds on the variables? Like, could they not see public information about the data set?
Right, so the size of the data set, we considered that to be a statistic they could release privately if they wanted to, so not assuming that that was necessarily public information. And then bounds, do you mean?
Like you asked the DP providers
Right.
to give also upper and lower bounds on each variable.
Right. So the providers, we asked them sort of not to look at their own, obviously they had access to their own data, but we asked them not to look at that when trying to set bounds for the variables, because that really shouldn't be based on the min and max of the variables. And then on the analyst side, they could see what the data provider had put in, but they sometimes didn't really have context about why those bounds were chosen, and if how they should alter them for their own purposes.
So, first, thank you. It's very interesting and I think relevant to this community. I want to ask about this line of research. So, in a sense, you took differential privacy as a given, and like it's an existing concept. This is what we want to implement, and you were researching, we call it the socializing of
Yeah, I think that's maybe a long-term goal of work like this is to think about, even relaxations of differential privacy in ways that address these challenges and that make it easier to use in practice. Or, possibly new understandings of technical notions of privacy that take all of this into account. I think that's hard to do. I think there will always be some sort of tensions between the theoretical framework and how people actually are currently using the data or want to use the data, but I think that's definitely helpful for both to be informed by each other.
I have a question about the changes to the workflow, I guess especially with the focus on the changes to the explanatory data analysis, or the exploratory data analysis part. So do you have a sense for how badly affected things would be if they didn't do exploratory data analysis? Because I feel like if the exploratory data analysis is very sample dependent rather than distribution dependent, then the results that you get might, the statistics that you get after doing exploratory data analysis might not reflect the distribution so much as the specific sample. So I guess I'm wondering what sorts of analyses people are doing and how badly things would be affected if they didn't.
Yeah, good question. I think the goal with, even having that as a benefit of differential privacy is to be able to understand what a data set is before going through the process of applying for it. So, so the idea is that, that doesn't consist of your whole analysis, but for you to even understand whether it's worth going through the process, it would be helpful to understand, kind of roughly what's in the data set, how these different variables, like the distributions of different variables and things like that. But I think even that step is currently hard to do without all of these, many of the contextualizing information about data sets that people may not have access to with differential privacy.